The idea of a black hole has always carried with it a mixture of fascination and unease. Imagine an object so compact and so massive that not even light can escape from its grasp. Once something crosses the invisible surface known as the event horizon, it is gone forever, at least as far as the outside universe is concerned. To most of us, this alone would be strange enough. But black holes have another, equally astonishing property. They can spin, not just slowly, not even like the steady rotation of a planet or a star, but in some cases, near the very speed of light itself. How is such a thing possible? And what does it mean for the fabric of the universe that surrounds them? When physicists first began to explore Einstein's general theory of relativity, the simplest solution was worked out by Karl Schwarzschild in 1916. His solution described a perfectly spherical black hole, one without any spin or electric charge. This was a kind of idealized object, useful as a starting point, but unlikely to exist in nature. Real stars rotate, and if one collapses under its own gravity to form a black hole, that rotation cannot simply disappear. Angular momentum, the physical quantity that describes spin, must be conserved. The moment we allow rotation into the picture, the geometry of space and time around the black hole becomes more complex, more twisted, more alive with motion. This rotating solution was worked out in 1963 by Roy Kerr, and ever since then the name Kerr black hole has been used to describe the rotating case. Unlike the quiet symmetry of the Schwarzschild black hole, the Kerr black hole drags space and time around with it. Imagine stirring a spoon through honey. The honey twists and swirls around the spoon. In a similar way, the space-time fabric around a rotating black hole is dragged by its motion. This is called frame dragging, and near the horizon it becomes extreme. The spin of a black hole influences almost everything about its behavior. It sets the position of the innermost stable orbit for matter spiraling inward. It affects how efficiently the hole can convert infalling matter into radiation. It shapes the enormous jets of plasma that we see shooting out of quasars and radio galaxies. It even changes the very geometry of the ergosphere, a region outside the horizon where no object can remain still relative to the distant universe. The spin of a black hole is not a minor detail. It is fundamental to the role black holes play as engines of energy in the cosmos. At first, spin was only a theoretical parameter, but in time, astronomers found evidence that many black holes are not only rotating, but spinning at incredible rates. In X-ray binaries, where a stellar mass black hole feeds off the gas of a companion star, signatures in the radiation hint at disks orbiting very close to the horizon, something only possible if the black hole is rotating rapidly. In active galactic nuclei, where supermassive black holes millions to billions of times the mass of our Sun blaze at the hearts of galaxies, the enormous energy output and narrow relativistic jets point to spin as the hidden power source. In some cases, careful measurements suggest that these cosmic behemoths are spinning at a fraction of the speed of light, so close to unity that we can barely distinguish them from the theoretical maximum. The mystery deepens when we ask how black holes gain and maintain such high spins. Do they inherit them from the stars that collapse to form them? Do they grow their spin through the relentless pull of accretion, drawing matter into their grip? Or do mergers between black holes, violent dances witnessed in gravitational waves, reshape spin into new extremes? The story of spin is really the story of angular momentum, of how the universe moves and balances its motions across cosmic time. To understand why some black holes spin so close to the speed of light, we must start with this most basic principle. The conservation of angular momentum is one of the most basic, yet powerful ideas in physics. It tells us that when no external torques act on a system, its spin remains constant. This principle is why a figure skater who pulls in their arms spins faster. By reducing the radius of rotation, the skater increases their speed to conserve angular momentum. Now imagine applying this same principle to a collapsing star, a body millions of times larger and vastly more massive than anything on Earth. When such a star exhausts its nuclear fuel and can no longer resist gravity, it collapses inward. The outer layers may explode outward as a supernova, but the core continues to contract. As it does so, the spin must increase. What was once a star rotating slowly in the void can become a neutron star or a black hole rotating at a dizzying rate. But here the comparison with a skater reaches its limits. For a skater, air resistance and friction eventually slow the spin. For a black hole, there is no such mechanism. Once it has acquired spin, it will keep that spin indefinitely unless something else intervenes. This is why astronomers believe that many black holes are born rotating. The collapse of the progenitor star does not erase spin, it magnifies it. When Roy Kerr discovered the exact mathematical form of a rotating black hole, he showed that its spin can be described by a dimensionless parameter, often called a star. If this parameter equals 0, the black hole is non-rotating. If it equals 1, the black hole is said to be extremal, spinning at the maximum rate allowed by general relativity. A spin greater than 1 would imply that the event horizon disappears, leaving a naked singularity, a possibility that most physicists believe is forbidden by the laws of nature. Thus, spin is not just a feature. It defines the very existence of the horizon. What is remarkable is that observations hint at black holes that are very close to this theoretical maximum. In stellar mass systems such as GRS 1915+105, spectral features in the X-ray data suggest an innermost orbit, almost brushing against the event horizon, which would only be possible for a black hole spinning at more than 95% of the speed of light. In the galaxy M87, whose central supermassive black hole was imaged directly by the Event Horizon Telescope, the presence of a colossal relativistic jet is most naturally explained by a rotating black hole acting like a dynamo, channeling rotational energy into streams of plasma that reach out tens of thousands of light years. The more we study these systems, the more spin appears to be at the center of their mysteries. Consider the ergosphere, that strange region outside the event horizon of a Kerr black hole. In this zone, frame dragging is so strong that all objects are forced to rotate in the direction of the black hole's spin. No particle can stand still with respect to the distant stars. If it tries, space-time itself carries it along. It is within this swirling region that processes like the Penrose mechanism can, at least in theory, extract energy from the spin of a black hole. Such processes may play a role in some of the most energetic events in the universe. All of this makes black hole spin not only a fascinating property, but a central driver of cosmic evolution. Galaxies light up because of accretion disks around spinning black holes. Jets punch through interstellar gas, altering the fate of galaxies because of the spin energy they release. Even gamma-ray bursts, the brightest flashes known, are believed in some cases to be powered by the collapse of a massive, rotating star that forms a fast-spinning black hole. Spin is not a footnote, it is a cosmic engine. Yet the question remains unresolved. Why do some black holes appear to rotate so close to the maximum speed, while others spin more slowly? What sets this distribution? Are the fastest spinners relics of special formation histories, or are they simply the lucky survivors of long episodes of accretion that pushed them to the brink? To address this, we must step back to the physics of angular momentum itself, to see how the story of spin begins in the life and death of stars, and so the mystery unfolds. From a simple idea in mechanics, applied on scales that dwarf imagination, arises one of the most extreme phenomena in the cosmos. The journey to understand black hole spin begins not with the black holes themselves, but with the stars whose collapse first gave them birth. Angular momentum is one of those quiet laws of physics that rarely draws attention, yet governs the motion of nearly everything in the universe. It is not as immediately dramatic as the idea of gravity pulling objects down, or as visually striking as light bending around a star. But without angular momentum, the cosmic order we see would collapse into chaos. Every planet, every star, every galaxy spins, and that spin is preserved with exquisite faithfulness across billions of years. To understand why some black holes rotate so swiftly, we must trace their story back to this principle. In classical mechanics, angular momentum is the product of an object's moment of inertia and its angular velocity. The concept seems abstract, but it is simply a measure of how much spin an object has and how difficult it is to change that spin. A child's toy top demonstrates it perfectly. Once set in motion, it resists any attempt to alter its axis of rotation. In the absence of friction, it would spin forever. On Earth, air resistance and contact with the floor slowly sap its energy, but in space, where there is no drag, the preservation of angular momentum is almost absolute. The stars themselves are born with spin. When clouds of gas and dust collapse under gravity to form a new star, any tiny initial rotation is amplified. This is the same principle that makes a skater spin faster when pulling in their arms. A cloud spanning light years across, slowly rotating in one direction, condenses into a sphere only a fraction of that size, and the rotation speeds up dramatically. Thus, every newborn star carries with it an angular momentum inherited from the motions of the interstellar cloud that gave it life. During the long main sequence stage of stellar life, rotation becomes a subtle player in the star's internal processes. Differential rotation, where the equator spins faster than the poles, stirs the stellar plasma. Magnetic fields couple the core to the outer layers. Stellar winds, streams of charged particles flowing into space, slowly drain angular momentum over millions or billions of years. Massive stars, with stronger winds, lose more spin than smaller ones. Still, even with these losses, the star remains a rotating body until its end. When the nuclear fuel in the core is exhausted, gravity takes over. The balance that kept the star stable collapses. For a massive star, this triggers a core collapse supernova. The outer layers are blown outward in a spectacular explosion, while the core implodes. What happens next depends on mass. A core just above the limit of stability may become a neutron star, an object only a few kilometers across, but so dense that a teaspoon of its matter would weigh billions of tons. More massive cores collapse all the way into black holes. Here, angular momentum shows its true power. The collapsing core shrinks from a radius of perhaps hundreds of thousands of kilometers to one measured in tens. The spin accelerates in a breathtaking increase. If angular momentum is conserved, even a modestly rotating progenitor star can give rise to a black hole, rotating near relativistic speeds. It is as if the universe takes the slow, graceful rotation of a star and hammers it into a whirlpool spinning almost at light speed. But the story is not so simple. Magnetic fields thread through the plasma, redistributing angular momentum between core and envelope. During collapse, stellar winds strip the outer layers, carrying spin away. Metallicity, the fraction of heavy elements in the star, influences these processes. A star rich in metals has stronger winds and may lose more angular momentum before collapse, producing a black hole with a more modest spin. A star poor in metals retains more mass and momentum, collapsing into a faster rotating black hole. These details mean that the final spin is not a simple reflection of the star's birth, but the outcome of a complex dance of forces over millions of years. The supernova mechanism itself also matters. If the collapse is asymmetric, with jets of material launched along certain axes, angular momentum can be redistributed in unexpected ways. In some models, fallback material raining down after the explosion adds further spin to the remnant. In others, the explosion strips away angular momentum more efficiently. Thus, while conservation of angular momentum is strict, the actual history of spin through collapse is subtle and layered with uncertainties. What remains clear is that black holes rarely begin life as motionless objects. They are almost always born rotating. Observations support this. In the case of Cygnus X-1, one of the first stellar mass black holes discovered, X-ray studies suggest a spin so high that it could only have come directly from the collapse of a massive star. The same appears true for many other stellar mass black holes in binary systems. The fingerprint of angular momentum is carved into their very birth. Yet this is only the beginning. A newborn black hole inherits the angular momentum of its parent star, shaped by winds, fields, and explosions. But a black hole is not a static relic. It is a cosmic engine connected to its environment. Once formed, it can draw in gas, stars, even other black holes. With each act of feeding or merging, its spin can change. Some will be slowed, others sped up, depending on the direction and manner of the material falling in. The spin a black hole is born with is only the first chapter in a longer story. To move deeper into this mystery, we must turn from collapse to growth. Beyond the violent birth of black holes lies the quieter but equally powerful process of accretion. Here, spin can be magnified toward the ultimate cosmic limit. As the lives of stars draw to their ends, the physics of angular momentum dictates the shape of their deaths. Consider a massive star, perhaps 30 or 40 times the mass of our Sun. Throughout its life, nuclear fusion builds heavier elements in the core while the star rotates steadily. As long as fusion burns, thermal pressure balances gravity. But when the fuel is gone, gravity wins. The core collapses inward, the outer layers explode outward, and the angular momentum of the inner regions is squeezed into a far smaller radius. If the collapse produces a neutron star, the result is often a rapidly rotating pulsar. Many pulsars rotate dozens of times per second, some even hundreds of times, sending beams of radio waves sweeping through space like cosmic lighthouses. This extraordinary speed is a direct consequence of angular momentum conservation. Shrinking from a sphere thousands of kilometers across to a body only about 20 kilometers wide means a massive increase in rotation rate. For black holes, the principle is the same, though the details are harder to study. Unlike pulsars, black holes have no solid surface and no emission of their own. We detect their properties indirectly by observing the behavior of matter around them, yet the same physics applies. If a progenitor star rotates, the black hole it leaves behind must also rotate, unless powerful forces strip away the angular momentum before collapse completes. The distribution of final black hole spins across the universe reflects the varied lives of stars. Stars born in environments rich with heavy elements lose more angular momentum through winds and magnetic braking, and so their remnants tend to spin less. Stars born in metal-poor environments, such as those that existed in the early universe, retain more angular momentum, and their remnants may spin more rapidly. This paints a picture in which cosmic history influences black hole spin. The further back we look, the more rapidly spinning black holes we might expect to find. The physics of angular momentum also influences whether a star forms a black hole directly, or whether it explodes first and then leaves behind a remnant. In some models, a star may collapse straight into a black hole with little or no explosion. In these cases, almost all the angular momentum of the star is swallowed directly. In others, a bright supernova expels the outer layers, taking spin with it, leaving a slower rotating remnant. Both outcomes may occur, depending on mass and composition. Astronomers see echoes of these processes in the diversity of black hole systems. Some stellar mass black holes in binaries appear to have inherited enormous spin, as if born that way. Others have more modest spin values, suggesting that their progenitors lost much angular momentum before collapse. Observations of X-ray spectra give us glimpses of these differences, allowing us to connect theoretical models with real systems across the galaxy. What unites them all is the inescapable rule of angular momentum conservation. From the scale of children's toys to the scale of dying stars, the principle holds without exception. In the case of black holes, it creates the conditions for some of the most extreme phenomena in nature. The story of angular momentum and stellar collapse is therefore not only the story of how black holes are born, but also the foundation for everything that comes afterward. Once a black hole exists, its spin becomes the key parameter determining how it interacts with the universe around it. The material it captures, the light it emits through accretion, the jets it hurls into intergalactic space, all are shaped by that spin. And spin is not fixed. It is the memory of a star's death, but also the evolving diary of a black hole's life. When matter falls in, when a star strays too close, when a companion feeds it gas, the spin changes. Sometimes it grows, sometimes it shrinks, but always it responds to the motions of the cosmos around it. The black hole may begin with the legacy of its parent star, but the universe will rewrite that legacy in the aeons to come. This brings us to the next part of the story, one that shifts from collapse to growth. For while stars give black holes their initial spin, it is accretion, the process of matter flowing steadily into their grasp that can push them to the brink of the ultimate cosmic speed limit. The quiet but relentless feeding of a black hole can transform it into one of the fastest spinners in the universe. If angular momentum from collapsing stars gives black holes their initial spin, accretion is the process that sculpts that spin into new extremes. Unlike the explosive drama of a supernova, accretion is a quieter, steadier, but no less powerful phenomenon. It is the long breath of cosmic evolution in which a black hole draws material toward itself, shaping not only its own destiny, but often the destiny of its host galaxy. Through this process, black holes can be spun up until their edges nearly graze the speed of light. Accretion begins when gas or dust finds itself within the gravitational influence of a black hole. Rather than falling straight in, the material typically has some sideways motion. That residual angular momentum prevents it from plunging directly and instead causes it to orbit. Over time, friction, turbulence, and magnetic stresses cause the gas to lose energy and spiral inward, but it cannot shed its angular momentum instantly. Instead, it forms a flattened, rotating disk, known as an accretion disk, that channels the flow inward while radiating energy outward. These disks are among the brightest sources in the universe. As gas compresses and heats, it emits light across the spectrum, from visible to X-rays. The closer matter comes to the event horizon, the hotter it becomes, reaching millions of degrees. Observing this radiation allows astronomers to map the conditions near the edge of the black hole, and in doing so, to estimate its spin. The geometry of the disk, the speed at which it can extend inward before plunging, the efficiency with which it radiates, all are tied to the black hole's rotation. In a thin disk, where matter settles into nearly circular orbits, the physics is well understood. Angular momentum is transported outward by magnetic instabilities, while mass flows inward. If this process continues for millions of years, the black hole can gain not only mass but also spin. In fact, theoretical work suggests that prolonged, steady accretion of matter orbiting in the same direction as the black hole's rotation can spin the hole up to near its maximum allowed value. The extremal limit at which the black hole rotates as fast as relativity permits becomes a possible outcome, not a distant idealization. The implications are profound. Black holes that live in environments rich with gas, such as the centers of young galaxies, may have been spun up to near light speed during epochs of furious accretion. This helps explain the tremendous power of quasars, those brilliant objects seen when the universe was only a fraction of its present age. Their central black holes, swallowing hundreds of solar masses of gas each year, could not shine so brightly without the added efficiency that high spin provides. In contrast, thick disk models describe situations where gas is not cool enough to settle into a thin layer, but instead puffs into a more toroidal structure. These flows are less efficient radiators, but they still transfer angular momentum. In either case, the long-term effect is to alter the black hole's spin according to the orientation and amount of material falling in. Observational evidence supports this picture. In stellar mass black holes within X-ray binaries, spin estimates often suggest that accretion has increased their rotation far beyond what collapse alone could produce. In some cases, black holes are inferred to spin at more than 90% of the maximum possible rate. For supermassive black holes, the statistics are more scattered, but many active galactic nuclei show signs of high spin, consistent with long histories of feeding from their host galaxies. But accretion does not always spin black holes up. If matter falls in from random directions, or if episodes of accretion alternate between prograde and retrograde orientations, the net effect can actually spin a black hole down. The direction matters. Accreting gas aligned with the black hole's existing spin adds to it, while gas with opposite orientation subtracts from it. Over cosmic time, a chaotic accretion history might lead to moderate spins rather than extremal ones. This may be why surveys find some supermassive black holes rotating less rapidly than others, even when their masses are enormous. Thus, the picture that emerges is not one of inevitability, but of diversity. Some black holes, fed steadily in one direction, are spun into near-perfect whirlpools. Others, subjected to chaotic flows, end up with spins in the middle range. Accretion, though steady in principle, can carve many possible fates. What remains constant is that it is one of the most powerful processes for altering the angular momentum of black holes after their birth. Yet accretion is not the only way. The universe has another, more violent path for reshaping spin, one written into the fabric of space-time itself. This path emerges when black holes meet, dance, and collide. Before we reach that, we must finish the story of accretion, exploring its full influence on the growth of spin and energy across cosmic history. Accretion is not only the mechanism by which black holes grow their mass and spin, it is also the way they reveal themselves to the universe. A perfectly isolated black hole, without matter to consume, is invisible. It radiates nothing. It betrays no sign of its existence, save for the gravitational pull it exerts on anything that wanders too close. But when a black hole begins to accrete, it transforms into a beacon. Gas swirling toward its event horizon heats up to millions of degrees, emitting X-rays and gamma rays that shine across galaxies. In some cases, the radiation outshines the combined starlight of billions of suns. And behind this extraordinary light lies the simple, relentless mechanics of angular momentum being transferred from one orbit to another as matter spirals inward. The efficiency of this process is extraordinary compared to other engines in the universe. A star, burning hydrogen into helium, converts only a fraction of 1% of its mass into energy. A black hole accreting matter can convert 10%, even up to 40% in the case of a maximally spinning hole, into radiant power. This staggering efficiency is possible because the innermost stable circular orbit of matter depends on spin. For a non-rotating black hole, that orbit lies at 6 times the gravitational radius. For a maximally rotating Kerr black hole, the orbit is as close as the event horizon itself. The closer matter can orbit before plunging in, the more gravitational energy it sheds as light. Thus, spin is not only a record of angular momentum, but a dial controlling how brilliantly a black hole can shine. This interplay between spin and accretion may help explain why quasars were so luminous in the early universe. Observations show that within the first billion years after the Big Bang, supermassive black holes had already grown to masses of millions and billions of solar masses. To achieve such growth so quickly, they must have accreted matter at extraordinary rates. And to shine as brightly as we see them today, many must also have been spinning rapidly, converting infalling matter into radiation with remarkable efficiency. Spin, in this sense, was not a byproduct, but a requirement for their brilliance. Yet accretion is not uniform across time or space. In some galaxies, gas streams steadily into the nucleus, feeding the central black hole for millions of years. In others, mergers or starbursts deliver gas in chaotic bursts. The history of spin in any given black hole is therefore tied to the cosmic history of its environment. A black hole in a calm, gas-rich galaxy may become a near-extremal spinner. One in a chaotic, merging galaxy may find its spin constantly tugged in different directions, leaving it with a moderate value. The diversity we observe today is written into these varied feeding histories. Astronomers continue to test these ideas by studying X-ray binaries in our own galaxy. These systems act as miniature laboratories, where accretion processes can be observed in detail. Gas stripped from a companion star forms a disk around the black hole, radiating strongly in X-rays. By analyzing the spectra and timing of these emissions, scientists can infer how close the gas comes to the horizon, and from that, estimate the spin. Some of these measurements reveal black holes rotating at more than 90% of the theoretical maximum. Others show more modest values. Each system tells a story of how much matter has been swallowed and from what direction. In the largest scales, accretion is also tied to the regulation of galaxies themselves. When a supermassive black hole accretes matter, it does not do so silently. The radiation and winds produced can heat and push back the gas in the galaxy, slowing or even halting the formation of new stars. The power of this feedback depends in part on spin, because higher spin black holes are more efficient at converting mass to energy. In this way, spin connects the smallest scales of space-time to the largest scales of galactic evolution. Accretion, then, is not just about feeding, it is about transformation. It transforms invisible black holes into cosmic lighthouses. It transforms gravitational energy into the brightest light in the universe. It transforms spin from an inherited trait of stellar collapse into an evolving property that can approach the limit of what physics allows. And it transforms galaxies, altering their growth and star formation over cosmic time. Still, even accretion has its limits. A black hole cannot spin beyond the Kerr bound, and while accretion can bring it close, relativity prevents it from crossing that line. To understand why, we must turn to the most violent black hole interactions of all. For in the universe, black holes do not only feed on gas, they also encounter each other, spiral together, and merge in cataclysmic events that shake the fabric of space-time itself. These collisions, revealed to us by gravitational waves, hold the next chapter in the story of spin. In the deep silence of the cosmos, black holes sometimes encounter one another. Most wander alone, but when two form a pair, bound by gravity, their fate is sealed. They orbit each other slowly at first, spiraling in over millions or billions of years, but with every revolution, energy leaks away in the form of gravitational waves. These ripples in the fabric of space-time, predicted a century ago by Albert Einstein, remained a theoretical whisper until the 21st century. When they were finally detected, they revealed not only the reality of gravitational waves, but also the hidden ballet of black holes colliding. Imagine two massive black holes locked in orbit. At large separations, they move serenely, circling one another as if caught in an endless dance. But as gravitational radiation carries energy away, the orbit shrinks. The black holes move faster, their velocities climbing to significant fractions of the speed of light. In the final seconds, they whirl around each other hundreds of times per second, then plunge together in a violent merger. The collision shakes space-time so powerfully that waves of distortion ripple outward, traveling across the universe, until, perhaps billions of years later, they wash across the detectors on Earth. For decades, physicists wondered whether these signals could ever be caught. Gravitational waves are unimaginably weak by the time they reach us, stretching and compressing space by less than the width of a proton. Yet in 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, accomplished the feat. The first detection came from a pair of stellar mass black holes colliding over 1 billion light-years away. The signal lasted only a fraction of a second, but encoded within it was the story of two black holes, their masses, their spins, and the moment of their union. Spin plays a critical role in these mergers. When two black holes spiral toward each other, their individual spins can align with the orbit or tilt against it. If aligned, the in-spiral is smoother, and the final remnant tends to spin faster. If misaligned, the orbital plane can wobble, producing distinctive modulations in the gravitational wave signal. From the shape and frequency of these signals, scientists can extract clues about the spin magnitudes and orientations of the colliding black holes. The discoveries so far reveal a surprising variety. Some mergers show evidence of black holes with little spin, suggesting that their progenitors lost angular momentum before collapse, or that chaotic histories left them rotating slowly. Others indicate higher spins, though rarely near the extremal limit. The distribution of spins observed by LIGO and its European partner Virgo has sparked debate. Are most black holes born with low spin, or are their spins randomized by repeated mergers and chaotic accretion? The data is still young, but it already points to a universe more complex than simple models predicted. Numerical relativity, the field that simulates mergers by solving Einstein's equations on supercomputers, has shown that the final spin of the merged black hole depends on both the masses and the initial spins of the pair. In many cases, the remnant is left spinning rapidly, though still below the maximum Kerr limit. The violent collision radiates away some angular momentum, carried off by gravitational waves themselves. What remains is a black hole more massive than either progenitor, and often spinning swiftly, as a single, unified entity. These mergers are not rare cosmic accidents. They are the natural outcome of stellar evolution in binary systems, or of dynamical encounters in dense star clusters. Over billions of years, they may contribute significantly to the population of black holes we see today. Each merger reshapes not only mass, but also spin, rewriting the history of angular momentum on cosmic scales. Yet the beauty of gravitational waves is that they let us witness this directly. Before their detection, black hole mergers were invisible. Now we can listen to their signals, like hearing the universe breathe. With each detection, we add another piece to the puzzle of how black holes gain, lose, and transform their spin. And behind all of this lies the deeper question: what does it mean for a black hole to spin close to the maximum allowed by nature? Why does relativity forbid spin beyond a certain bound? To answer this, we must examine the theoretical frontier of rotating black holes, where physics stretches to its limits, and the concept of extremal spin emerges. As gravitational wave astronomy matures, the catalogue of black hole mergers grows longer, and with each new signal, the universe whispers more of its secrets about spin. Already, dozens of confirmed events show us that mergers are not exotic rarities, but rather frequent milestones in the cosmic story. Some involve black holes only a few tens of times the mass of our Sunday. Others hint at intermediate mass black holes, with hundreds of solar masses, bridging the gap between stellar remnants and the supermassive giants at galactic centers. In every case, the pattern of waves encodes information about how these objects rotate. What the data suggest is both simple and profound. Most black holes detected through mergers do not appear to be spinning at the extreme values that accretion alone might produce. Instead, many have moderate spins, or even values, consistent with very slow rotation. This aligns with models where black holes in binaries are born from stars that shed angular momentum through winds, magnetic fields, and mass transfer before collapse. It also fits with the idea that mergers themselves tend to average out spin, producing remnants that are fast, but not extremal. The universe, it seems, prefers balance rather than extremes, though exceptions exist. The role of spin orientation adds another layer of intrigue. In some events, the gravitational wave signals suggest that the spins of the two black holes were aligned with the orbital plane, a sign they may have evolved together as a binary star pair before collapse. In others, the spins seem misaligned, as if the black holes formed separately and later paired up in a dense stellar cluster. Misalignment produces precession, a wobbling of the orbital plane that imprints itself on the waveform. By measuring these delicate modulations, astronomers can reconstruct not just how fast black holes spin, but also how their cosmic lives brought them together. When the collision reaches its climax, the final moments are a triumph of relativity. The two horizons touch, fuse, and settle into a single, quivering black hole. The newborn horizon oscillates, ringing like a struck bell, before settling into stability. These ring-down vibrations radiate energy outward as gravitational waves, their frequencies determined by the mass and spin of the remnant. In these dying echoes, scientists find a clean signature of the final spin, often confirming the predictions of numerical simulations to remarkable precision. One of the most fascinating outcomes of these studies is that mergers can create black holes spinning near the upper bounds allowed by relativity, though never beyond. The energy radiated away in the waves prevents the final spin from exceeding the Kerr limit. Even in the most favorable alignments, some angular momentum must be lost to spacetime itself. It is as though nature enforces a strict law, drawing a line that no black hole may cross. The detection of gravitational waves has transformed what once was speculation into direct observation. For decades, physicists spoke of black hole mergers as mathematical possibilities. Now, with instruments stretching across continents, humanity can literally hear the sound of spacetime as black holes collide. And embedded in those sounds are the fingerprints of spin, telling us which black holes rotate slowly, which rotate swiftly, and how their collisions forge new identities. But as remarkable as this is, mergers are not the whole story. They reveal much about the evolution of spin, but they also point us toward the ultimate boundary. What happens when a black hole approaches the very edge of allowed rotation? What lies at the brink of the extremal limit? And why can no black hole surpass it? These questions lead us to the next chapter, where theory confronts the very foundations of relativity and defines the Kerr bound, the cosmic speed limit for spin. Every law of nature seems to carry a boundary, a point beyond which it refuses to go. For black holes, this boundary is encoded in their spin. As strange as it may sound, there exists a cosmic speed limit not for objects moving through space, but for the rotation of space-time itself. This limit is called the Kerr bound, and it defines the maximum spin a black hole can ever possess. To understand this boundary, we must return to the mathematics of the Kerr solution, the exact description of a rotating black hole found by Roy Kerr in 1963. In his equations, the rotation of a black hole can be expressed as a dimensionless parameter, the ratio of its angular momentum to the maximum value permitted for its mass. This parameter, often written as a star, ranges from 0 for a non-rotating black hole to 1 for a maximally rotating one. If a star equals 1, the black hole is called extremal. What happens if a black hole could somehow spin faster than this limit? The equations predict that the event horizon would vanish, exposing the singularity itself to the outside universe. This hypothetical object is known as a naked singularity, a point of infinite density without the protective cloak of a horizon. For decades, physicists have debated whether such objects could exist. Most suspect they cannot. The cosmic censorship conjecture, proposed by Roger Penrose, suggests that nature always hides singularities behind horizons, shielding the rest of the universe from their raw infinities. If this principle is correct, then no process can spin a black hole beyond the Kerr bound. The extremal limit is more than a mathematical curiosity. It shapes the very structure of space-time around a black hole. As spin increases, the event horizon shrinks slightly, while the ergosphere expands. Frame dragging grows stronger, twisting space-time more tightly. The innermost stable orbit for matter falls closer to the horizon, allowing higher energy extraction from accreting gas. In the extremal case, the efficiency of energy release approaches an astonishing 40% of the rest mass energy of the accreted matter. By comparison, nuclear fusion releases less than 1%. Extremal black holes are, in principle, the most efficient engines in the universe. Yet despite these dramatic properties, reaching extremality appears impossible in practice. Every process that adds spin also adds mass, and relativity conspires so that the ratio never exceeds 1. Even carefully tuned accretion, with gas flowing steadily in the same direction for billions of years, will asymptotically approach, but never cross the Kerr bound. In fact, subtle effects like radiation, emitted by the disk, can carry away angular momentum, preventing the spin from ever reaching perfection. Nature seems to whisper, this far and no further. Observations suggest that some black holes come tantalizingly close. The microquasar GRS 1915+105 has been measured to spin at more than 98% of the maximum allowed rate. Other candidates, such as certain quasars and X-ray binaries, also appear near extremality, but none has yet been shown to cross the boundary. Whether any real black hole in the universe achieves true extremal spin remains an open question. The possibility of extremal black holes has fascinated physicists for another reason as well. Near such objects, space-time exhibits exotic properties. Time itself appears to dilate infinitely near the horizon. The ergosphere becomes an arena for strange processes, where particles can split, one falling inward and the other escaping with more energy than it entered. Theoretical frameworks like string theory and ADS-CFT duality have explored extremal black holes as laboratories for uniting gravity with quantum mechanics. Extremality, in this sense, is not just an astrophysical boundary, but a window into fundamental physics. Still, the boundary holds. In every realistic scenario we know, black holes may approach the Kerr limit, but never exceed it. The cosmos enforces the rule. Yet to test this, We must measure black hole spins with precision, a task far from simple. The challenge of observing and confirming whether a black hole lies near the extremal limit leads us naturally into the next chapter, where light and gravity become our tools for measurement. The notion that black holes cannot exceed the Kerr bound is one of the most striking examples of how general relativity draws lines in the sand. It is not merely that we have not observed a spin greater than unity. The mathematics itself tells us that if such a value were reached, the geometry of spacetime would break in ways that defy the theory. Without an event horizon, the singularity would be exposed. Causality itself could unravel, with closed time-like curves permitting violations of the normal flow of time. This is why the conjecture of cosmic censorship remains such a central principle. To protect the universe from paradox, the horizon must endure, and so the spin must remain beneath the limit. Physicists have attempted thought experiments to test whether the Kerr bound can be violated. What if a carefully aimed particle with enormous angular momentum were fired into a nearly extremal black hole? Would the impact tip it over the edge? Calculations suggest that the black hole resists. Either the particle cannot be captured, or energy losses ensure the horizon remains intact. Accretion flows, too, have been tested in theory. While they can spin a hole up very close to extremality, subtle feedback such as radiation torque remove enough angular momentum to keep the bound secure. Even mergers, some of the most violent events in the cosmos, radiate angular momentum away in gravitational waves, ensuring the final remnant respects the limit. This limit has profound implications. It means that nature provides us with a ceiling for the rotational energy stored in black holes. In turn, this caps the maximum power that can be extracted through mechanisms like Blandford's Znajek, where magnetic fields tap into spin to launch relativistic jets. While these jets can be staggeringly powerful, illuminating galaxies across millions of light years, they still operate within the boundary defined by Kerr. The universe grants us brilliance, but within carefully defined rules. Observationally, we find evidence that black holes press close to this frontier. Systems like Cygnus X1 and the quasar in the galaxy Ferrel 9 suggest spins of more than 90% of the maximum. In some active galactic nuclei, the data hint at values that might be as high as 98 or 99%. These measurements are not trivial. They depend on careful modeling of spectral lines, disk temperatures, and relativistic effects. Yet the consistency of the results across multiple methods strengthens the conclusion. Some black holes are indeed spinning near the cosmic edge. Whether any black hole has achieved the exact extremal state remains unknown. Some theorists argue that extremality may be approached asymptotically, but never reached in finite time. Others leave open the possibility that in the chaotic environment of galaxy mergers or accretion bursts, a black hole might cross the threshold, if only briefly. If such an object exists, it would challenge both observation and theory, forcing us to confront the limits of relativity itself. But until evidence demands it, the Kerr bound stands as one of the most reliable barriers in astrophysics. Extremal black holes are more than astrophysical curiosities. They are testbeds for quantum gravity. In string theory, extremal black holes provide models where entropy, area, and microscopic states can be calculated explicitly, offering glimpses into how information might be preserved across horizons. In the ADS-CFT correspondence, extremal horizons play key roles in dual descriptions of spacetime and quantum fields. For many physicists, the extremal case is not just a limit to be respected, but a gateway to deeper truths about the unification of physics. And so we arrive at a curious point in the story. We know that spin cannot exceed the Kerr bound. We know that real black holes can come astonishingly close. But to determine just how close any given black hole lies, we must rely on the delicate art of measurement. Spin is not a quantity we can touch or weigh directly. It must be inferred from the light of accretion disks, from the patterns of X-rays, and from the gravitational waves that ripple through spacetime. To move forward, we must leave theory behind and enter the realm of observation, where light and gravity become our instruments. and where the challenge of measuring spin takes center stage. For all the beauty of theory, the true test of physics lies in observation. It is one thing to describe black holes with equations and predict the boundaries of their spin, but quite another to measure that spin in the universe. Black holes hide their secrets behind horizons from which no information can escape, yet light from the matter around them and the waves of space-time they create when they collide provide indirect but powerful clues. Measuring spin is one of the great triumphs of modern astrophysics, achieved through ingenuity, persistence, and technology stretched to its limits. The first method relies on the glow of accretion disks. As matter spirals inward, it heats to millions of degrees and emits X-rays. Within this radiation lie signatures shaped by relativity. One of the most useful is the iron K-alpha line, a feature produced when iron atoms in the disk emit photons at a characteristic energy. Near a black hole, this line is distorted. Photons climbing out of the deep gravitational well lose energy, shifting the line toward the red. Those emitted from gas, moving toward us, are blue shifted, while those from receding gas are red shifted. The result is a broadened, skewed profile that encodes the geometry of the inner disk. The location of the innermost orbit, which depends directly on spin, leaves its mark in this shape. Another approach is the continuum fitting method. Here, astronomers model the thermal emission from the disk as a whole. The disk radiates like a multicolored surface, with hotter inner regions and cooler outer ones. By comparing the spectrum to models of how disks should behave at different spins, the radius of the innermost stable orbit can be inferred. This requires independent knowledge of the black hole's mass and distance, as well as the inclination of the disk. But when these are known, the method provides one of the most direct ways to estimate spin. In both techniques, the critical link is that the position of the innermost stable orbit shrinks with increasing spin. For a non-rotating black hole, it lies 6 gravitational radii from the center. For a maximally rotating one, it lies just outside the horizon. Matter orbiting this close produces hotter, more energetic radiation, shifting the spectral shape. The degree of broadening or hardening in the X-ray spectrum is thus a window into the hidden rotation of the black hole. Quasi-periodic oscillations, rapid flickers of X-ray brightness seen in some accreting systems, may also carry information about spin. These oscillations occur at frequencies linked to orbital motions near the horizon. If their origin is understood, they could reveal not only the mass of the black hole, but also the rate of its spin. Though the interpretation remains debated, these rhythms of light may one day provide another powerful probe. Gravitational waves add a new dimension to measurement. When black holes collide, the waves carry imprints of their spins. During the inspiral, if the spins are misaligned with the orbital axis, the plane of the orbit precesses, modulating the waveform. In the final merger and ringdown, the frequency of the waves depends on the mass and spin of the remnant. By comparing observed signals to massive banks of theoretical waveforms generated by numerical relativity, scientists can estimate spins directly from the gravitational radiation itself. This has opened a new observational frontier, independent of electromagnetic light. None of these methods is perfect. Each carries uncertainties, and each depends on assumptions. The structure of the accretion disk, the alignment of our line of sight, the calibration of detectors, all affect the results. This is why multiple methods are often applied to the same system, and why disagreement between them is treated not as failure, but as an opportunity to refine models. Despite the challenges, the growing body of spin measurements paints an increasingly clear picture. Black holes are not all the same. Some rotate lazily, some whirl furiously, and their spins tell stories about their birth, growth, and cosmic role. The effort to measure spin is not merely an exercise in astrophysical curiosity. Spin determines how efficiently a black hole can power luminous accretion, and how strongly it can drive jets that reshape galaxies. To measure spin is to measure the heartbeat of a cosmic engine. It is to uncover not only what black holes are, but what they do. And so the light of accretion and the waves of space-time become our translators, carrying across the horizon's silence the information we cannot otherwise obtain. With each new measurement, we move closer to understanding why some black holes spin so close to the speed of light, and what that means for the universe itself. The challenge of measuring spin lies not only in the physics but also in the limitations of our instruments. X-ray telescopes must detect faint signals against backgrounds of noise. They're detectors sensitive enough to separate narrow features in the spectrum. Space-based observatories like Chandra, XMM Newton, and NuSTAR have been crucial, orbiting above Earth's atmosphere, where high-energy light can be observed without absorption. These instruments give us the raw data, but the real work begins afterward, in the careful modeling of what those photons mean. Each spectrum is a puzzle, requiring comparison with simulations of how disks behave under the rules of relativity. Take the case of Cygnus X1, one of the best-studied stellar mass black holes in our galaxy. Observations of its X-ray spectrum reveal an iron line broadened almost beyond recognition. The shape of this line indicates that gas in the disk must be orbiting very close to the event horizon, which can only happen if the black hole is spinning rapidly. Independent continuum fitting confirms the result, placing its spin at more than 95% of the maximum. Here, light acts as a tracer of motion, in a realm where no direct image can yet be made. The Event Horizon Telescope, which imaged the shadow of the black hole in M87, provides another form of measurement. While the image itself does not directly reveal spin, the shape and brightness of the crescent structure depend on how the accretion flow interacts with the rotating spacetime. Future refinements may allow spin to be extracted from such images more reliably, especially with the next generation array that will sharpen the view of horizons across the universe. Gravitational wave detectors add their own perspective. Since the first detection in 2015, dozens of binary black hole mergers have been observed. In many of these, spin has been measured to varying degrees of accuracy. Some events show clear evidence of aligned spins, while others reveal hints of misalignment. The precision is improving as detectors grow more sensitive and as more events are collected. When the space-based observatory LISA launches in the next decade, it will detect waves from supermassive black hole mergers, providing a completely new window on spin across cosmic time. Despite these advances, uncertainties remain. Disks may not always behave in the simple ways our models assume. Magnetic fields, turbulence, and radiation pressure can complicate their structure. Gravitational wave signals can be ambiguous when spins are small or misaligned, requiring long stretches of data to tease out subtle effects. But this is the nature of science. Each difficulty becomes a chance to refine theory and improve measurement. Already, the fact that different methods sometimes agree gives confidence that we are reading the signatures correctly. The broader pattern that emerges is clear. Some black holes spin furiously, close to the cosmic limit. Others turn slowly, perhaps because their progenitors shed angular momentum, or because their histories of accretion were chaotic. Supermassive black holes in quasars often show high spins, consistent with long periods of feeding in a steady direction. Stellar mass black holes in binaries display a wide range, some likely born rotating rapidly, others spun up later by accretion. Every measurement adds a brushstroke to the portrait of spin in the universe. It is not a simple picture. There is no single law dictating how fast black holes rotate. Instead, spin reflects history, the collapse of a star, the flow of matter, the merger of companions. By learning to measure spin, we learn to read this history, turning black holes from silent enigmas into storytellers of cosmic evolution. In the end, what these measurements provide is not only confirmation of relativity's predictions, but also insight into how black holes shape their surroundings. A black hole with high spin can power jets that pierce galaxies, regulating the birth of stars. A slower one may be quieter, less efficient, less influential. The ability to measure spin is therefore not just about characterizing a property of exotic objects. It is about uncovering one of the most important levers by which the universe writes its grand design. And so we reach a turning point. Having learned how spin can be measured, we are ready to ask the deeper question: what does spin allow black holes to do? If rotation is a reservoir of energy, how does nature tap into it? And how does that energy shape galaxies, quasars, and the universe at large? To answer, we must step from measurement into consequence, from knowing spin to seeing what spin can unleash. Spin is not only a property of black holes, it is a source of power. In the strange geometry of a rotating horizon lies one of the most efficient engines nature has ever created. Matter falling into a black hole can release extraordinary amounts of energy, not merely because of gravity, but because of spin itself. Rotation turns the black hole into a kind of dynamo, capable of driving jets of plasma across interstellar space, igniting quasars, and shaping the evolution of entire galaxies. The first and most direct way spin enhances energy output is through accretion efficiency. As we have seen, the position of the innermost stable orbit depends on spin. For a non-rotating black hole, matter can orbit only at a radius 6 times the gravitational radius before plunging inward. For a maximally rotating Kerr black hole, prograde orbits can extend almost to the horizon itself. This means that more gravitational energy is released as heat and radiation. The difference is dramatic. A non-rotating black hole converts about 6% of the rest mass of infalling matter into energy. A near-extremal spinner can convert close to 40%. The spin thus acts as a multiplier, turning accretion disks into dazzling beacons. But spin does more than brighten disks. Through magnetic fields, it can actually extract rotational energy directly from the black hole itself. This is the essence of the Blandford-Znajek mechanism, proposed in 1977. Imagine magnetic field lines threading the ergosphere of a rotating black hole, anchored in the surrounding accretion disk. As space-time drags, the field lines twist, and this twisting drives electric currents that channel energy outward. The result is a pair of tightly collimated jets, streams of plasma accelerated to nearly the speed of light, launched perpendicular to the disk. These jets can extend for thousands, even millions of light years, carrying energy from the central black hole into the wider universe. Observations confirm the link between spin and jets. In radio galaxies, the most powerful jets are thought to be powered by rapidly rotating supermassive black holes. The correlation is not perfect, for environment and magnetic fields also play roles, but the presence of extreme jets in systems where spin is measured to be high is strong evidence. In microquasars, smaller cousins within our galaxy, similar processes are seen on a smaller scale. The scaling of these phenomena across many orders of magnitude in mass suggests a universal mechanism. Spin may also be central to gamma-ray bursts, the brief but brilliant explosions that mark the deaths of massive stars. In some scenarios, the collapse of a rapidly rotating stellar core forms a black hole surrounded by a dense accretion disk. The spin of the new black hole, tapped by magnetic fields, drives jets that punch through the star and blast into space, releasing as much energy in seconds as the Sun will in its entire lifetime. Though many details remain uncertain, spin is widely considered a key ingredient in these most extreme of cosmic fireworks. The influence of spin does not end at the scale of individual events. By powering jets and winds, black hole spin feeds back into galaxies. Jets deposit energy into the interstellar medium, heating gas and sometimes preventing it from cooling to form new stars. In galaxy clusters, the jets of central supermassive black holes inflate enormous cavities in the hot plasma, regulating star formation on scales of hundreds of thousands of light years. This feedback loop, in which black hole spin helps determine how galaxies grow, is now seen as a cornerstone of cosmic evolution. Thus, spin is not an isolated parameter, but a driver of structure in the universe. A rapidly rotating black hole is not just a silent, whirling void. It is an engine that lights up galaxies, launches streams of matter across intergalactic space, and sculpts the very distribution of stars. To understand spin is therefore to understand one of the most profound connections between the smallest and largest scales of existence. But the story is not complete without the evidence. How do we know these jets, bursts, and feedback processes truly depend on spin and not merely on environment or accretion rate? The answer lies in the careful comparison of systems across cosmic scales, in patterns that reveal spin as the hidden factor. And in these comparisons, we begin to see that the fastest spinners leave the loudest marks on the universe. The link between spin and energy output becomes clearest when astronomers study populations of black holes across different environments. In some stellar mass systems within our galaxy, where the mass and accretion rates can be measured with relative confidence, those black holes that show the highest spins also produce the most powerful jets. The relationship is not absolute, for accretion rate and magnetic field strength play crucial roles. But the trend is persistent enough to suggest that spin is a decisive factor. The black holes with rapid rotation seem able to tap into an additional reservoir of energy, amplifying what accretion alone would provide. On the grandest scales, supermassive black holes at the centers of galaxies tell a similar story. In the most luminous quasars, jets stretch across intergalactic space, sometimes spanning hundreds of thousands of light years. Their narrow collimation, their enormous power, and their persistence over millions of years suggest a stable mechanism connected to the deep structure of the black hole itself. Models of the Blandford-Znajek process, which converts spin into jet power, align remarkably well with the observed energetics. It is as though the rotation of the black hole, locked within the horizon, finds a way to influence the cosmos far beyond its reach. These jets are not merely spectacular in themselves. They shape the evolution of galaxies. By heating and stirring the gas that would otherwise collapse into stars, jets regulate the growth of stellar populations. Galaxies with overactive black holes often show suppressed star formation, their interstellar reservoirs disrupted by the outflows. In clusters of galaxies, where supermassive black holes lie at the hearts of giant ellipticals, the jets carve vast cavities in the surrounding hot plasma, cavities that can be observed directly in X-ray maps. In this way, the spin of a single object, a few light hours across, can influence structures spanning millions of light years. Even in more transient events, spin makes its presence known. Gamma-ray bursts, lasting mere seconds, carry away energies that rival the output of entire galaxies. The most convincing models involve newly formed black holes with high spin, driving jets through collapsing stars. Without rotation, the mechanism for such explosive collimation is far less efficient. Spin, again, appears as the hidden lever that turns collapse into detonation. What is remarkable is the unity of this principle across scales. From stellar mass microquasars producing jets a few light years long, to supermassive black holes inflating bubbles in galaxy clusters, the same physics applies. Spin plus magnetic fields plus accretion creates jets. And while the details differ, the universality of the process is one of the most compelling patterns in astrophysics. The broader implication is that spin is not simply an internal parameter of black holes, but a cosmic actor. It dictates how bright a system can be, how violently it can expel energy, and how far its influence extends. The galaxy that surrounds a black hole is not an isolated environment. It is part of a feedback loop where the spin of the black hole shapes the galaxy's destiny, and the galaxy's gas supply shapes the spin in turn. We stand, then, at an extraordinary realization. Something as intangible as angular momentum, preserved from the collapse of stars and sculpted by accretion and mergers, becomes the driving force behind the grand architecture of galaxies. The spin of a black hole is a thread woven into the fabric of cosmic evolution, tying together the physics of the smallest scales with the fate of the largest. But to see this principle in action, we must turn to the actual evidence of extreme spinners. Which black holes in the universe show us this power most clearly? What do their spins tell us about the conditions that created them? The next chapter will take us into case studies of observed systems, from stellar mass binaries in our galaxy to quasars blazing at the edge of the universe, where black holes spin near the very limits set by nature. The idea of black holes spinning close to the speed of light might seem abstract, a theoretical boundary drawn from equations. But astronomy is not content with theory alone. Across the sky, in binary systems, in distant quasars, and at the centers of galaxies, we find black holes whose observed behavior reveals astonishingly rapid rotation. These extreme spinners are not just curiosities, They are natural laboratories, where the laws of relativity, the mechanics of accretion, and the feedback into galaxies all converge. One of the first stellar mass black holes where extreme spin was detected lies in the system known as Cygnus X1. Discovered in the 1960s as a strong X-ray source, it became one of the earliest confirmed black hole candidates. Decades of observations eventually revealed that its spectrum bore the unmistakable signs of a rapidly spinning horizon. Careful analysis of the iron line profile and continuum fitting showed that the inner edge of the accretion disk must lie extraordinarily close to the event horizon, possible only if the black hole spins at more than 95% of the maximum allowed rate. Cygnus X1 thus became a benchmark, the first in a series of stellar mass black holes, found to spin with near relativistic speed. Even more extreme is the system known as GRS 1915+105, a microquasar in our galaxy. This black hole, about a dozen times the mass of our Sun, is notorious for its violent variability. Jets stream from it, and its X-ray emission flickers in complex rhythms. Spectral analysis indicates a spin exceeding 98% of the maximum value. In effect, it is one of the fastest known spinners in the cosmos, a natural test case for the physics of near-extremal black holes. Observations of its behavior have provided key insights into how spin couples with accretion and jet production on humanly observable timescales. At the other end of the mass scale, supermassive black holes show equally dramatic results. The giant in the galaxy M87, imaged directly by the Event Horizon Telescope, powers a jet thousands of light years long. While the image itself cannot provide a precise spin value, models of the jet's stability and energy output point to a rapidly rotating black hole. The sheer scale of this jet, sustained for millions of years, almost certainly requires the rotational energy of a Kerr black hole being tapped through magnetic fields. Here, spin is not only an intrinsic property but a galaxy-shaping force. Quasars, the most luminous persistent sources in the universe, also bear the imprint of extreme spin. Their power cannot be explained by accretion alone. The efficiency required to convert matter into light at such dazzling levels is achievable only if their central black holes are spinning rapidly. X-ray spectroscopy of several quasars has confirmed this, showing broadened iron lines and spectral features consistent with high spin. These observations stretch across billions of light years, meaning we see quasars as they were when the universe was young. The implication is profound. Many of the earliest supermassive black holes were already spinning close to the cosmic limit. These examples highlight a key truth. Spin is not evenly distributed. Some black holes rotate slowly, others moderately, but a select group pushes near the theoretical maximum. The reasons for this diversity are complex. Some inherit high spin from their progenitor stars. Others are spun up by long, steady episodes of accretion. Still, others achieve high spin through carefully aligned mergers. What unites them is that their behavior reveals the fingerprints of rotation in unmistakable ways. The story of extreme spins is not only about individual objects, but also about statistics. Surveys of black holes across populations are beginning to show patterns. Among stellar mass black holes, high spin appears relatively common, perhaps because their progenitors collapse directly without shedding too much angular momentum. Among supermassive black holes, spin seems linked to history. Those in quiet, gas-rich galaxies often show higher values, while those in turbulent, merging galaxies show a wider spread. These patterns, drawn from hundreds of measurements, begin to transform anecdote into evidence, painting a more complete portrait of spin in the universe. Yet, uncertainties remain. Measuring spin is difficult, and results depend on models of disks and jets that are still being refined. Different methods sometimes give different answers for the same system. But science thrives on such challenges. Each disagreement is a clue, a pointer toward better understanding. With new telescopes and instruments, the catalogue of measured spins will grow, and the picture will sharpen. Already, however, it is clear that black holes spinning near the speed of light are not rare oddities, but recurring characters in the cosmic play. The existence of such extreme spinners forces us to confront the deepest questions about black hole growth. How did they reach these speeds? Why does nature allow some to come so close to the limit? And what does this distribution tell us about the history of galaxies and the universe itself? To answer, we must treat spin not just as a property of individual objects, but as a tool for tracing cosmic evolution across time. The true power of observational astronomy is its ability to turn abstract theory into living evidence. Extreme spins, once imagined only as mathematical curiosities, now appear again and again in the sky, revealed by the light of matter and the rhythm of gravitational waves. Each detection is like a fragment of a larger story, and together they reveal a universe where black holes regularly push against the very limits of relativity. Consider the statistical surveys of stellar mass black holes in our galaxy. Using X-ray spectroscopy and continuum fitting, astronomers have assembled a catalogue of spin measurements across more than 24 systems. The results are striking. A significant fraction of these black holes spin at more than 80% of the maximum allowed value. Some even approach 99%. Others, however, show only modest or slow rotation. The diversity underscores that spin is not predetermined, but sculpted by the histories of stars and binaries. In systems where black holes accrete steadily from companion stars over millions of years, spin can grow to near extremal values. In those where accretion is chaotic or limited, spin remains lower. For supermassive black holes, the story is even more compelling. X-ray studies of active galactic nuclei, where gas swirls furiously into central black holes millions or billions of times the mass of the Sun, reveal that many spin rapidly. Some of the most luminous quasars require spin values close to extremal to explain their brightness. These objects, seen as they were billions of years ago, tell us that high spin was already common in the early universe. The implication is that feeding black holes efficiently was a key part of their rapid growth. Without spin enhancing the efficiency of accretion, it is difficult to explain how such massive black holes formed so quickly after the Big Bang. The Event Horizon Telescope adds to this picture, not with spectra, but with images of horizons themselves. The ring-like shadow of M87 star and the compact glow of Sagittarius A star both offer glimpses of accretion flows bending light around rotating horizons. While precise spin values remain uncertain, the very presence of stable jets in M87 strongly suggests a rapidly rotating black hole. As imaging sharpens in the years to come, we may one day read spin directly from the silhouettes of black holes themselves. Gravitational waves provide a complementary approach. While most detected mergers so far involve black holes with modest spins, a few events hint at rapid rotation, especially when misalignments cause the orbital plane to wobble. As detectors become more sensitive, the catalogue will grow into hundreds and then thousands of mergers. Among them will surely be examples of extreme spin, perhaps even binaries where both members whirl at near light speed before colliding. These signals will provide independent confirmation of what electromagnetic observations already suggest, that nature is unafraid to push black holes to the edge of the Kerr bound. Yet despite the progress, mysteries remain. Why do some populations favor high spin, while others show wide distributions? Why do some supermassive black holes maintain rapid spin over billions of years, while others slow down? The answers lie in the details of accretion, mergers, and feedback, processes that unfold across cosmic timescales. Observations are beginning to separate these influences, but the picture is not yet complete. What is clear is that spin is far from incidental. It shapes the efficiency of light, the power of jets, the regulation of galaxies. Observations of extreme spinners provide direct evidence of relativity's predictions in action, confirming that the geometry of Kerr spacetime is not just mathematics, but physical reality. The universe contains black holes spinning at 99% of the speed of light, and their presence affects the fate of galaxies themselves. As we step back, a pattern emerges. The study of extreme spins bridges the smallest scales of physics with the largest scales of structure. By observing these cosmic whirlpools, we learn not only about black holes, but about the growth of galaxies, the evolution of the early universe, and the boundaries of relativity itself. Spin, once hidden beyond horizons, becomes a tool for cosmic archaeology, a way to read the history of matter, energy, and time. But the story does not end here. Observations tell us that black holes spin at extraordinary speeds. The next question is what those spins mean for the universe at large. Can spin be used as a tracer of cosmic history, revealing how galaxies merged and grew? Can it serve as a key to unlocking the co-evolution of black holes and galaxies? To explore this, we must take a step further outward, from individual objects to the cosmic web itself, and ask how spin can become a tool for cosmology. Black holes are not merely exotic objects hidden in the shadows of galaxies. They are record keepers. Locked within their spin is the memory of how they formed, how they grew, and how their galaxies evolved around them. To measure spin is to uncover a piece of cosmic history, a tracer of events that otherwise would be lost in time. In this way, spin becomes more than a parameter of astrophysics. It becomes a tool for cosmology. The principle is simple, but powerful. A black hole can gain mass through many routes, but each leaves a different imprint on its spin. If it grows primarily through steady accretion of gas orbiting in the same direction, the spin rises, approaching near extremal values. If it grows through chaotic accretion, with gas falling in from random directions, the spin fluctuates and remains moderate. If it grows through mergers with other black holes, the outcome depends on the alignment of spins and orbits. A merger of two aligned, rapidly spinning black holes produces a fast spinner. A merger of two misaligned or slowly rotating ones produces a more modest remnant. Thus, by measuring the spin of a black hole today, we glimpse the history of how it came to be. This idea is most powerful for supermassive black holes at the centers of galaxies. These titans, weighing millions to billions of times the mass of the Sun, grow over billions of years through a mixture of accretion and mergers. Their spins carry the record of which process dominated. In galaxies where we measure rapid spins, the implication is long epochs of calm, coherent accretion. In galaxies where spins are moderate, the history may have been turbulent, marked by frequent mergers or misaligned feeding. Spin measurements therefore connect directly to questions of galaxy evolution. How did galaxies grow? How did they merge? And how did their central black holes shape their fate? Surveys of active galactic nuclei already reveal intriguing trends. Some luminous quasars, seen when the universe was only a few billion years old, show evidence of high spin. This suggests that coherent accretion dominated in the early universe, perhaps fueled by abundant cold gas streams flowing into young galaxies. By contrast, some present-day galaxies harbor supermassive black holes with moderate spins, consistent with growth through mergers during the more chaotic later epochs of cosmic structure formation. Spin, in this way, reflects the cosmic environment, a silent witness to the universe's changing dynamics. Spin also connects to feedback, the process by which black holes influence their galaxies. A high-spin black hole can power stronger jets and more efficient energy release, altering star formation and gas dynamics. Thus, spin does not just record history, it actively shapes it. Galaxies and black holes co-evolve, each influencing the other, and spin is the bridge between them. To trace spin is to trace the intertwined destinies of matter on scales from horizons to clusters of galaxies. The implications reach even further. Spin may help us probe the growth of structure in the universe itself. If future surveys measure the distribution of spins across thousands of supermassive black holes, we could map how different growth channels operated across cosmic time. Did the early universe favor smooth accretion, spinning black holes to near the limit? Did later epochs favor mergers, producing a broader spread? The answers could illuminate how the large-scale cosmic web funneled matter into galaxies, and how galaxies in turn shaped the growth of their central engines. Spin is also a testing ground for cosmological theories. If measurements consistently revealed spins beyond the Kerr bound, it would signal a failure of relativity and point to new physics. If certain environments produced unexpected distributions, it could challenge models of galaxy formation. Spin thus acts as both a tracer and a test. guiding us toward a deeper understanding of the cosmos. But the promise of spin as a cosmological tool depends on future instruments. The next generation of X-ray observatories, like Athena, will provide sharper spectra to measure spin with greater precision. The space-based gravitational wave observatory, LISA, will detect mergers of supermassive black holes across billions of light-years, extracting spin directly from the waves of spacetime. The next-generation Event Horizon Telescope will image more black hole shadows, perhaps allowing spin to be read in the bending of light itself. Together, these tools will transform spin from a property measured in dozens of objects to one mapped across the universe. In this way, spin may become as fundamental to cosmology as redshift or luminosity, a measurable quantity that reveals the history of matter, energy, and structure. What once seemed a hidden detail of invisible objects becomes a new lens through which to view the universe. Spin can also reveal how galaxies themselves were assembled. When two galaxies collide, their central black holes eventually sink toward the middle of the merged system and form a binary. After long spirals inward, they coalesce, producing a new black hole whose spin reflects the geometry of the merger. If the galaxies approached along aligned axes, the resulting remnant may spin rapidly. If they collided chaotically, the spin may end up lower. Thus, the spin of a supermassive black hole today holds within it a memory of ancient galactic encounters. In this way, astronomers use spin like a fossil, a relic imprinted with the story of cosmic structure formation. Even the orientation of spin tells a story. Black holes aligned with their host galaxies suggest long histories of smooth, orderly accretion. Misaligned spins, revealed by warped disks or precessing jets, hint at past disruptions or chaotic feeding. These orientations matter because they determine how energy is fed back into the galaxy. A jet aligned with the galactic axis can pierce straight through, affecting large volumes of gas. A misaligned jet may dissipate its energy more quickly, altering the pattern of feedback. Thus, spin orientation is not only a clue to history, but also a key factor in shaping galactic futures. Spin also intersects with some of the deepest questions in physics. If black holes are truly described by only three properties, mass, spin, and charge, then measuring spin becomes one of the few ways we can probe the nature of these objects. By comparing measured spins with theoretical predictions, we test the very foundation of general relativity. If ever we found evidence for spin values beyond the Kerr bound, it would challenge everything we know about horizons and singularities. Though no such violation has been seen, the very act of measuring spin on cosmic scales functions as an ongoing test of relativity in its most extreme regime. The promise of the future is immense. Athena will survey X-ray spectra with unprecedented resolution, allowing scientists to measure spins of black holes across cosmic distances. LISA will listen to the mergers of supermassive black holes, extracting precise spin values from the ringing of space-time. The next generation Event Horizon Telescope will sharpen its focus, mapping light around horizons with detail fine enough to reveal rotational effects. Each of these missions will expand our sample size from dozens to thousands, transforming spin from a niche measurement into a cornerstone of cosmology. With these tools, we will be able to trace how spin evolved across cosmic epochs. Did the earliest galaxies feed their black holes with smooth flows of cold gas, producing high spins across the board? Did the era of galaxy mergers later reduce spins through chaotic accretion? How did feedback from spinning black holes regulate star formation and shape the large-scale structure of the universe? Each measurement adds a data point to these questions, gradually turning speculation into knowledge. In this sense, spin is not only a property of black holes, but a cosmic chronicle. It records the lives of stars, the feeding of galaxies, the collisions of cosmic giants. By learning to read spin, we learn to read the universe's diary, a record written not in ink, but in the whirling of space-time itself. And though the measurements are still young, they point to a future where spin will become a standard cosmological tool, as fundamental to mapping the universe as redshift or cosmic microwave background radiation. But as with every frontier in science, the closer we approach clarity, the more questions arise. Spin tells us much, but not everything. Even as we begin to map its distribution across the cosmos, uncertainties remain about the processes that drive it and the ultimate limits of our theories, which leads us into the final part of our journey, the enduring mysteries. To complete the story, we must confront what we know, what we suspect, and what still lies hidden in the shadows. The story of black hole spin carries us from the collapse of stars to the shaping of galaxies, from the predictions of Einstein's equations to the ripples of space-time detected a century later. We have seen how angular momentum, that quiet law of physics, magnifies itself in collapse, how accretion sculpts spin toward the cosmic limit, how mergers reshape it, and how spin in turn powers light, jets, and feedback across the universe. We have measured spin in stellar binaries and quasars, in microquasars flickering in our galaxy, and supermassive giants billions of light years away. The evidence is clear. Black holes do not simply exist. They whirl, often at speeds approaching the ultimate limit allowed by relativity. And yet, even with all we know, black hole spin remains a frontier of mystery. Observations show us some black holes spinning at 99% of the maximum, but none has ever been proved to reach the exact extremal state. Theory insists the Kerr bound cannot be crossed, but whether it can be reached precisely or only approached asymptotically is still uncertain. Some argue that subtle effects like radiation drag or magnetic braking always prevent perfect extremality. Others wonder if the chaotic environments of the early universe might have spun some black holes closer to the edge than we dare believe. The truth remains hidden, behind horizons we cannot penetrate. Beyond the classical picture lies the quantum. At the smallest scales, general relativity collides with the rules of quantum mechanics, and spin may hold clues to their reconciliation. Extremal black holes, in particular, appear again and again in theoretical physics. In string theory, they provide test cases where entropy can be calculated and matched to microscopic states. In ADS-CFT duality, extremal horizons serve as windows into the correspondence between gravity and quantum fields. To understand spin at the limit may therefore be to glimpse the unification of the great theories that govern our universe. Even the question of information, the black hole information paradox, connects to spin. If black holes evaporate through Hawking radiation, what becomes of the information encoded in their rotation? Can spin be radiated away, or does it leave some indelible imprint on the universe? The resolution of this paradox remains one of the most pressing challenges in physics, and spin is woven into its fabric. The observational frontier, too, pushes forward. With each new instrument, we measure spin in more systems, with greater precision, across wider ranges of cosmic time. Yet with each measurement come new puzzles. Why do some populations of black holes favor high spin, while others scatter across values? Why do some galaxies harbor near extremal engines, while others do not? Do the fastest spinners we see today reflect calm feeding histories, or are they survivors of violent but precisely aligned mergers? Spin becomes not only a parameter, but a question, a key that opens one door only to reveal another. In this way, spin embodies the essence of scientific discovery. It is at once known and unknown, measurable yet mysterious, concrete in its effects, yet elusive in its ultimate meaning. It is a boundary we can describe mathematically, yet one we may never see crossed. It is both a driver of cosmic evolution and a mirror of processes long past, telling us how stars died, how galaxies grew, and how the universe assembled itself. We stand now at the edge of knowledge. Beyond this edge lies speculation, theory, and the promise of future discovery. Black hole spin has already reshaped our understanding of the cosmos. What secrets it still holds remain for the next generations of instruments, theorists, and explorers to uncover. If black hole spin is a measure of how matter collapses and how galaxies grow, it is also a reminder of how much we do not yet know. We can observe the flicker of X-rays from hot disks, the flick of relativistic jets piercing galaxies, the trembling of space-time, as horizons merge. We can model the equations, simulate the mergers, and calculate the efficiencies. Yet the moment we press against the boundaries, when a black hole spins so fast that the horizon nearly brushes the speed of light, we feel the limits of human knowledge. The Kerr bound is a line written in the language of relativity, but whether it is a wall of stone or a veil of mist remains uncertain. Perhaps nature keeps the secret hidden forever. Perhaps no black hole ever quite touches extremality, each one forever slowed by the tiny loss of radiation, the chaotic jostle of accretion, or the shedding of angular momentum into gravitational waves. Or perhaps, in the early universe, when conditions were raw and violent, some black holes did spin at the very edge, briefly inhabiting the state of extremality before settling back. If such objects exist, they would be the purest testbeds of relativity ever made, but also the most difficult to confirm, locked behind horizons that no light escapes. Even more tantalizing is the possibility that spin carries messages from physics not yet discovered. If quantum gravity reveals itself anywhere, it may do so at the horizon of an extremal black hole where space-time and quantum fields intertwine. In those hidden depths may lie answers to the paradox of information, to the mystery of how gravity and quantum mechanics coexist, and to the fate of the universe itself. Spin may be the key not only to understanding black holes, but to uniting the laws of the cosmos. As we look forward, instruments like Athena, LISA, and the next generation Event Horizon Telescope will give us sharper eyes and deeper hearing. They will measure spins across the universe, tracing histories of galaxies and stars that no other tool can reach. Each new measurement will be a step closer to unveiling whether nature dares to approach the absolute. Each will remind us that the most fundamental truths are often written in the smallest details, like the whirling of space-time around a collapsed star. In the end, black hole spin is both a fact and a mystery. It is a measurable quantity that shapes galaxies, powers jets, and confirms relativity. Yet it is also a frontier that hints at deeper laws, at horizons of knowledge not yet crossed. Some black holes spin near the speed of light, but none may ever exceed it. Whether the universe itself has more to say about this boundary remains the greatest open question of all. And so we close on the edge of the horizon, gazing at objects that spin faster than anything else in nature, engines that light galaxies and carve the cosmos, yet remain hidden in silence. To measure their spin is to measure not only their motion, but the rhythm of the universe itself. Perhaps, when the final questions are answered, we will find that the story of spin is not only about black holes, but about the nature of reality itself, a story still waiting, deep in the shadows, to be told. Spin by itself is powerful, but it does not act in isolation. The universe is threaded with magnetic fields, from the surfaces of stars to the vast expanses between galaxies. When the whirling space-time of a rotating black hole couples with these invisible fields, the result is one of the most dramatic displays of energy known to science. Jets burst outward, lobes of radio emission inflate, cavities in plasma stretch across hundreds of thousands of light years. Spin, when married to magnetism, becomes a force that ties black holes not only to their host galaxies, but to the larger cosmic web itself. Magnetic fields are born in plasma, carried along with charged particles like threads woven into flowing fabric. Around a black hole, gas in the accretion disk is ionized, and its motion naturally generates fields. These fields arc and twist as the disk rotates, sometimes reconnecting explosively, sometimes stretching outward into interstellar space. When the disk surrounds a spinning black hole, the twisting of space-time itself winds these field lines like a cosmic dynamo. In the ergosphere, where nothing can remain still, field lines are dragged relentlessly around the black hole, storing rotational energy like a coiled spring. The Blandford-Znajek mechanism describes how this stored energy can be released. As field lines twist, they accelerate particles along their axes, launching twin jets outward at nearly the speed of light. The power of these jets depends not only on the strength of the fields, but on the spin of the black hole itself. The faster the spin, the more efficiently rotational energy can be converted into electromagnetic outflows. Thus, the brightest radio galaxies, whose jets extend for millions of light years, are thought to be powered by the fastest spinners in the universe. Observations bear this out. The galaxy Centaurus A shows enormous radio lobes inflated by jets that must have been active for tens of millions of years. In Perseus and Virgo clusters, cavities in the hot intracluster gas mark the footprints of jets that carved space on scales dwarfing galaxies. These features are not random explosions. They are long-lived, steady processes, consistent with black hole spin acting through magnetic fields to regulate the flow of energy from the heart of galaxies into intergalactic space. On smaller scales, microquasars like GRS 1915+105 show the same principle at work. In this system, jets flicker on and off in rhythm with changes in the accretion flow, a miniature version of the processes that shape entire galaxies. The connection between spin, magnetism, and jets holds across 8 orders of magnitude in mass, from stellar black holes to giants weighing billions of suns. The physics is universal, a single thread connecting the small with the vast. But the influence of spin and magnetism does not stop at galaxies. Jets launched by spinning black holes carry energy far beyond their hosts, heating intergalactic gas and influencing how structures grow in the cosmic web. Simulations of large-scale structure formation show that feedback from active black holes is essential to reproduce the observed distribution of galaxies. Without it, galaxies would form too quickly, too abundantly, consuming gas before clusters and filaments could take shape. With it, the balance is restored. Spin, channeled through magnetism, becomes a regulator of the entire cosmic ecosystem. We live, then, in a universe where the rotation of horizons drives the growth of galaxies, clusters, and even the scaffolding of the cosmic web. The spin of a black hole, though hidden behind an event horizon, extends its influence across millions of light years. It is a reminder that in physics, no parameter is ever truly local. Spin resonates outward, its effects felt in the distribution of galaxies across the sky itself. But as always, questions remain. How precisely do magnetic fields couple to horizons? How do turbulent flows in disks regulate the strength and orientation of jets? Why do some rapidly spinning black holes launch powerful jets, while others remain quiet? These puzzles lie at the forefront of research, where observations and simulations race to capture the full complexity. What is certain is that spin and magnetism together are cosmic architects, shaping not only the fates of individual galaxies, but the large-scale pattern of the universe. To trace their interplay is to understand how the smallest and largest structures in existence remain bound together by hidden forces. When astronomers map the radio sky, they see giant structures that often dwarf the galaxies that host them. These are radio lobes, balloon-like clouds of charged particles inflated by jets from supermassive black holes. Each lobe can span hundreds of thousands of light years, shining in radio waves as particles spiral along magnetic field lines. The energy stored in these lobes is staggering, equivalent to the combined output of trillions of stars. Yet their origin lies in the invisible spin of a black hole only a few light hours across. In clusters of galaxies, the evidence of spin-driven magnetism is even more dramatic. Hot gas fills the space between galaxies, glowing in X-rays. Jets launched by central black holes carve vast bubbles in this plasma, cavities visible in X-ray maps like fingerprints pressed into cosmic fog. These cavities suppress cooling, preventing gas from condensing into new stars, and maintain the balance of cluster ecosystems. Without them, galaxies in clusters would form too many stars, too quickly, and the structures we see today would look entirely different. The spin of black holes, through their magnetic outflows, becomes a regulator of cosmic star formation. Yet not all black holes behave the same. Some spin rapidly, but produce little or no jet activity. Others, with moderate spins, generate strong outflows. The difference likely lies in the strength and geometry of magnetic fields. Simulations suggest that only when fields are organized and amplified in a magnetically arrested disk does the full power of spin become available. In such cases, the black hole acts like a cosmic dynamo, extracting rotational energy to launch jets. When fields are weaker or more chaotic, spin remains locked within the horizon. Thus, spin is a necessary but not sufficient condition for cosmic jets. Magnetism must provide the bridge. This interplay adds richness to our picture of the universe. Spin alone explains much, but spin plus magnetism explains more. The diversity of active galaxies, the presence or absence of jets, the variation in feedback strength. Observationally, we see correlations between radio loudness and spin, but not perfect ones. The imperfections are not contradictions but clues, reminders that cosmic processes rarely reduce to a single parameter. They are symphonies, and spin is one instrument among many, amplified by the strings of magnetism. On even larger scales, spin and magnetism may contribute to the connectivity of the cosmic web itself. Jets inject energy into intergalactic filaments, stirring magnetic turbulence and spreading metals forged in stars. In this way, spinning black holes help distribute the ingredients of planets and life across the universe. Though horizons are silent, their influence echoes across cosmic distances, leaving imprints in the chemistry of galaxies and the patterns of the web. Future instruments promise to reveal this connection in greater detail. Next-generation radio arrays will map jets and lobes with unprecedented clarity. X-ray observatories will measure the cavities carved in clusters with greater precision. Polarization studies will trace the geometry of magnetic fields around spinning horizons, testing the models of magnetically arrested disks. Together, these observations will transform our understanding of how spin and magnetism shape the universe on every scale. In the end, the lesson is profound. The rotation of a black hole, a property hidden behind an event horizon, reaches out to shape galaxies, clusters, and cosmic structures. Through the agency of magnetic fields, spin becomes a cosmic architect, building patterns that stretch across millions of light years. To study spin in this context is to see the unity of the universe, where the smallest and the largest are bound by invisible threads. And yet, even here, mysteries remain. Do the fastest spinners always produce the strongest feedback, or are there hidden variables we have yet to grasp? Is spin the ultimate driver of the cosmic web, or simply one contributor among many? These questions ensure that the story of spin, even as it unfolds into larger scales, remains unfinished. And that brings us to the final chapter, where we look forward into the future, to the discoveries yet to come, and to the deeper truths that spin may one day reveal. The study of black hole spin is still young. For most of human history, the very existence of black holes was debated, dismissed by some as a mathematical oddity. Only in the last century did they move from speculation to observation, from equations scribbled in chalk to images captured by telescopes. Now we not only know they exist, we can measure their mass, glimpse their shadows, and even weigh the speed of their rotation. And yet, the greatest discoveries still lie ahead. The future of spin is a story waiting to be written, a frontier where observation and theory meet to test the deepest laws of nature. The coming decades will be transformative. Space missions already on the horizon promise to sharpen our view of spinning black holes. Athena, the advanced telescope for high-energy astrophysics, will revolutionize X-ray spectroscopy, resolving spectral lines with clarity never before achieved. With its eyes, we will measure the spins of hundreds, perhaps thousands of black holes, building a map of rotation across the universe. Where today we have scattered case studies, tomorrow we will have a census, a statistical survey that reveals patterns invisible to us now. On another front, the Laser Interferometer Space Antenna, or LISA, will listen to gravitational waves from the mergers of supermassive black holes. These signals, stretching for hours or days as titans spiral together, will encode spin with exquisite precision. We will learn how giant black holes grew, whether through steady accretion or chaotic collisions, and how their spins evolved over cosmic time. LISA will not only hear the universe, it will give us a soundtrack of cosmic rotation. Meanwhile, the next generation Event Horizon Telescope will sharpen its focus, imaging horizons with greater detail and across more frequencies. With these instruments, we may be able to read spin directly from the bending of light around black holes, tracing how rotating spacetime sculpts the glow of accretion flows. Sagittarius A star and M87 star were only the beginning. Dozens of horizons may one day be resolved, each carrying its own signature of spin. Beyond observation, theory pushes forward. Supercomputer simulations grow more sophisticated, modeling the turbulence of accretion, the structure of magnetically arrested disks, and the launching of jets. Numerical relativity continues to refine predictions of merger remnants, connecting waveforms to spins with increasing accuracy. At the cutting edge, theorists explore extremal black holes in string theory and quantum gravity, using them as testbeds for the unification of physics. The frontier of spin is not only about galaxies and quasars, it is also about the deepest questions of reality. Even the paradoxes remain. Does information escape from evaporating black holes? If so, how does spin play a role in encoding it? Can the evaporation of a near-extremal black hole reveal something about the fabric of spacetime itself? These questions blur the line between astrophysics and fundamental physics, showing that spin is not only a tool for describing the cosmos, but a bridge to the mysteries of existence. The future of spin, then, is not only about measurement, but about meaning. Each observation adds precision to our models, but also adds depth to our understanding of how the universe works. Spin will guide us not only to the history of black holes, but to the nature of space-time, energy, and information itself. The instruments of tomorrow will give us answers, but they will also give us new mysteries. This is the pattern of science. Every horizon reached reveals another beyond it. When Athena measures spins across galaxies, we will ask why some populations are rapid, while others are slow. When LISA listens to the deep bass of merging giants, we will ask what hidden histories those signals conceal. When sharper images of horizons emerge, we will ask whether light itself can betray subtler truths about the rotation of spacetime. Spin will remain a teacher, but also a trickster, always telling us just enough to keep us searching. In the more distant future, technologies yet unborn may let us probe black holes in ways we can scarcely imagine. Perhaps fleets of interferometers orbiting the sun will measure gravitational waves with such precision that we can map every twist of spin in the observable universe. Perhaps new detectors of neutrinos or exotic particles will reveal signatures of black hole environments shaped by rotation. Perhaps quantum computers will model the evaporation of near-extremal black holes, showing how spin entwines with the fate of information. Each possibility stretches our imagination, but all are bound by the same truth. Spin lies at the heart of the unknown. Even the question of extremality will linger. Will we ever prove that nature can create a truly extremal black hole, spinning exactly at the limit of relativity? Or will every case remain just shy, like an asymptote never reached? If one were found, what would it mean? Would it be stable? Or would quantum effects unravel it in moments? The answers, if they come, will force us to rethink not only astrophysics, but physics itself. And then there are the deeper mysteries. Could spin itself be a more fundamental property than mass, a feature of spacetime woven into its very fabric? Some theorists have speculated that the rotation of black holes might connect to the rotation of the universe at large, though evidence remains elusive. Others wonder if spin could help unify gravity with the quantum world, serving as a bridge between the continuous geometry of relativity and the discrete states of quantum mechanics. Whether these ideas bear fruit or not, they show how spin continues to inspire visions that reach beyond current science. What is certain is that the story of spin is far from finished. We have traced it from the collapse of stars to the shaping of galaxies, from the twisting of jets to the whisper of gravitational waves, from the Kerr bound to the edge of quantum theory. And still, questions multiply. Spin remains both a fact and a mystery, both a parameter we can measure and a puzzle we cannot yet solve. Perhaps this is the greatest gift of black hole spin. It forces us to face the unknown, not with despair, but with wonder. It reminds us that even in a universe we think we understand, there are edges where certainty dissolves and mystery reigns. Some black holes spin near the speed of light, their horizons brushing the cosmic limit, but none reveal their secrets fully. They turn in silence, unseen yet felt, shaping galaxies and clusters, carrying within their motion the rhythm of the universe itself. And so we end where we began, with awe. Spin is not only a property of black holes, it is a story of motion, energy, and time, a record of the universe written in the whirl of space-time. As we look forward, we know that the future of spin will carry us deeper into the unknown, toward horizons both physical and philosophical. What we will find there, no one can yet say. Perhaps the final truth is that the mystery itself is the message that in the turning of black holes, the cosmos whispers to us that its greatest secrets are still to come. Black holes are not merely exotic objects hidden in the shadows of galaxies. They are record keepers. Locked within their spin is the memory of how they formed, how they grew, and how their galaxies evolved around them. To measure spin is to uncover a piece of cosmic history, a tracer of events that otherwise would be lost in time. In this way, spin becomes more than a parameter of astrophysics. It becomes a tool for cosmology. The principle is simple, but powerful. A black hole can gain mass through many routes, but each leaves a different imprint on its spin. If it grows primarily through steady accretion of gas orbiting in the same direction, the spin rises, approaching near extremal values. If it grows through chaotic accretion, with gas falling in from random directions, the spin fluctuates and remains moderate. If it grows through mergers with other black holes, the outcome depends on the alignment of spins and orbits. A merger of two aligned, rapidly spinning black holes produces a fast spinner. A merger of two misaligned or slowly rotating ones produces a more modest remnant. Thus, by measuring the spin of a black hole today, we glimpse the history of how it came to be. This idea is most powerful for supermassive black holes at the centers of galaxies. These titans, weighing millions to billions of times the mass of the Sun, grow over billions of years through a mixture of accretion and mergers. Their spins carry the record of which process dominated. In galaxies where we measure rapid spins, the implication is long epochs of calm, coherent accretion. In galaxies where spins are moderate, the history may have been turbulent, marked by frequent mergers or misaligned feeding. Spin measurements therefore connect directly to questions of galaxy evolution. How did galaxies grow? How did they merge? And how did their central black holes shape their fate? Surveys of active galactic nuclei already reveal intriguing trends. Some luminous quasars, seen when the universe was only a few billion years old, show evidence of high spin. This suggests that coherent accretion dominated in the early universe, perhaps fueled by abundant cold gas streams flowing into young galaxies. By contrast, some present-day galaxies harbor supermassive black holes with moderate spins, consistent with growth through mergers during the more chaotic later epochs of cosmic structure formation. Spin, in this way, reflects the cosmic environment, a silent witness to the universe's changing dynamics. Spin also connects to feedback, the process by which black holes influence their galaxies. A high-spin black hole can power stronger jets and more efficient energy release, altering star formation and gas dynamics. Thus, spin does not just record history, it actively shapes it. Galaxies and black holes co-evolve, each influencing the other, and spin is the bridge between them. To trace spin is to trace the intertwined destinies of matter on scales from horizons to clusters of galaxies. The implications reach even further. Spin may help us probe the growth of structure in the universe itself. If future surveys measure the distribution of spins across thousands of supermassive black holes, we could map how different growth channels operated across cosmic time. Did the early universe favor smooth accretion, spinning black holes to near the limit? Did later epochs favor mergers, producing a broader spread? The answers could illuminate how the large-scale cosmic web funneled matter into galaxies. and how galaxies in turn shape the growth of their central engines. Spin is also a testing ground for cosmological theories. If measurements consistently revealed spins beyond the Kerr bound, it would signal a failure of relativity and point to new physics. If certain environments produced unexpected distributions, it could challenge models of galaxy formation. Spin thus acts as both a tracer and a test, guiding us toward a deeper understanding of the cosmos. But the promise of spin as a cosmological tool depends on future instruments. The next generation of X-ray observatories, like Athena, will provide sharper spectra to measure spin with greater precision. The space-based gravitational wave observatory, LISA, will detect mergers of supermassive black holes across billions of light-years, extracting spin directly from the waves of space-time. The next generation Event Horizon Telescope will image more black hole shadows, perhaps allowing spin to be read in the bending of light itself. Together, these tools will transform spin from a property measured in dozens of objects to one mapped across the universe. In this way, spin may become as fundamental to cosmology as redshift or luminosity, a measurable quantity that reveals the history of matter, energy, and structure. What once seemed a hidden detail of invisible objects becomes a new lens through which to view the universe. Spin can also reveal how galaxies themselves were assembled. When two galaxies collide, their central black holes eventually sink toward the middle of the merged system and form a binary. After long spirals inward, they coalesce, producing a new black hole whose spin reflects the geometry of the merger. If the galaxies approached along aligned axes, the resulting remnant may spin rapidly. If they collided chaotically, the spin may end up lower. Thus, the spin of a supermassive black hole today holds within it a memory of ancient galactic encounters. In this way, astronomers use spin like a fossil, a relic imprinted with the story of cosmic structure formation. Even the orientation of spin tells a story. Black holes aligned with their host galaxies suggest long histories of smooth, orderly accretion. Misaligned spins, revealed by warped disks or precessing jets, hint at past disruptions or chaotic feeding. These orientations matter because they determine how energy is fed back into the galaxy. A jet aligned with the galactic axis can pierce straight through, affecting large volumes of gas. A misaligned jet may dissipate its energy more quickly, altering the pattern of feedback. Thus, spin orientation is not only a clue to history, but also a key factor in shaping galactic futures. Spin also intersects with some of the deepest questions in physics. If black holes are truly described by only three properties, mass, spin, and charge, then measuring spin becomes one of the few ways we can probe the nature of these objects. By comparing measured spins with theoretical predictions, we test the very foundation of general relativity. If ever we found evidence for spin values beyond the Kerr bound, it would challenge everything we know about horizons and singularities. Though no such violation has been seen, the very act of measuring spin on cosmic scales functions as an ongoing test of relativity in its most extreme regime. The promise of the future is immense. Athena will survey X-ray spectra with unprecedented resolution, allowing scientists to measure spins of black holes across cosmic distances. LISA will listen to the mergers of supermassive black holes, extracting precise spin values from the ringing of space-time. The next generation Event Horizon Telescope will sharpen its focus, mapping light around horizons with detail fine enough to reveal rotational effects. Each of these missions will expand our sample size from dozens to thousands, transforming spin from a niche measurement into a cornerstone of cosmology. With these tools, we will be able to trace how spin evolved across cosmic epochs. Did the earliest galaxies feed their black holes with smooth flows of cold gas, producing high spins across the board? Did the era of galaxy mergers later reduce spins through chaotic accretion? How did feedback from spinning black holes regulate star formation and shape the large-scale structure of the universe? Each measurement adds a data point to these questions, gradually turning speculation into knowledge. In this sense, spin is not only a property of black holes, but a cosmic chronicle. It records the lives of stars, the feeding of galaxies, the collisions of cosmic giants. By learning to read spin, we learn to read the universe's diary, a record written not in ink, but but in the whirling of space-time itself. And though the measurements are still young, they point to a future where spin will become a standard cosmological tool, as fundamental to mapping the universe as redshift or cosmic microwave background radiation. But as with every frontier in science, the closer we approach clarity, the more questions arise. Spin tells us much, but not everything. Even as we begin to map its distribution across the cosmos, uncertainties remain about the processes that drive it and the ultimate limits of our theories, which leads us into the final part of our journey, the enduring mysteries. To complete the story, we must confront what we know, what we suspect, and what still lies hidden in the shadows. Among all the effects of spin, none is stranger than its grip on time itself. Black holes do not merely bend space, they bend the very flow of moments. Around a rotating horizon, the familiar arrow of time can warp, twist, and in some cases, threaten to fold back on itself. To explore spin is therefore to step into the frontier of reality, where cause and effect, past and future, may blur. The key to this lies in frame dragging, a phenomenon predicted by general relativity and confirmed by experiments in Earth's orbit. When a massive object spins, it drags space-time around with it, like a spoon swirling honey in a cup. Around Earth, this effect is tiny, measured by the Gravity Probe B experiment in 2004. Around a rotating black hole, it dominates. In the ergosphere, no object can remain still. Even light itself is forced to rotate with the black hole's spin, carried forward by the whirl of space-time. Frame dragging alters the very geometry of time. Paths that would normally be impossible become possible. Particles can gain energy by splitting, with one fragment falling inward and the other escaping with more than it began. This Penrose process shows that rotation can be tapped as a source of energy, but it also shows that time in the ergosphere is not like time elsewhere. It is bent and twisted, reshaped by spin into something less familiar. At the extreme, theories suggest that spinning black holes might allow closed time-like curves, loops in space-time, where an object could return to its own past. Such curves appear in certain solutions of relativity, including the Kerr geometry, when spin exceeds the limit of stability. In these scenarios, causality itself is at risk. Events could cause themselves, paradoxes could arise, and the normal order of time could collapse. Most physicists believe that nature forbids such violations, protecting chronology through mechanisms we do not yet understand. Still, the possibility remains embedded in the mathematics, a haunting reminder of how spin stretches the fabric of reality. Even without paradox, spin changes our experience of time near horizons. To a distant observer, objects falling into a black hole appear to slow, their clocks ticking ever more slowly as they approach the event horizon. Around a spinning black hole, this dilation becomes even more pronounced, influenced by the dragging of space-time. To the infalling observer, nothing seems amiss. Time flows normally. But to the universe outside, their descent becomes frozen, stretched into eternity. Spin therefore creates a duality of time, two perspectives that cannot be reconciled, except by accepting relativity's strange rules. Spin also shapes the arrow of time in astrophysics. Jets launched from rotating black holes carry energy outward, influencing galaxies for millions of years. In this sense, spin writes long-term histories, guiding the flow of cosmic evolution. Yet, inside the horizon, where time and space trade roles, the very meaning of future and past dissolves. Rotation deepens this dissolution, making the horizon not only a boundary of space, but also a boundary of time. To contemplate spin is to contemplate time's fragility. The laws we take for granted, that causes precede effects, that moments flow in one direction, are not immutable. They are emergent, preserved by the structures of space-time. And in the whirl of a rotating black hole, these structures stretch to their breaking point. Spin reminds us that time itself is not absolute, but part of the fabric of the universe, woven and rewoven by gravity. The possibility that spin could bend time itself raises questions that reach beyond physics into philosophy. If causality can break down near rotating horizons, what does that mean for the universe as a whole? Could nature ever permit loops of time, or are they forever hidden behind horizons, inaccessible to observers? The cosmic censorship conjecture suggests that the singularities where such effects might occur are always veiled. Yet the mathematics leaves traces of their existence, as though hinting at a deeper reality beneath the surface. In practice, spin already alters time in ways we can observe. Satellites around Earth measure tiny drags on their orbits due to our planet's rotation. Gyroscopes on Gravity Probe B recorded subtle twists in the direction of space-time, confirming Einstein's prediction. If such small bodies can bend time so delicately, how much more profound must the effect be near a black hole spinning at nearly the speed of light? There, minutes and hours would stretch into eternity for distant observers, while for the infalling traveler, time would flow normally until the horizon is crossed. The contradiction is only apparent. Both views are correct, each bound to its own frame. The edge of reality is reached when we consider extremal rotation. At the Kerr limit, the geometry of space-time becomes so warped that the structure of time approaches singular behavior. The horizon thins, the ergosphere widens, and the pathways of light itself circle in endless loops. Some theorists suggest that in these conditions, quantum effects may intervene to preserve causality, perhaps creating new states of matter or new geometries of space-time. Others propose that time itself may become fuzzy, not a single line, but a spectrum of possibilities. Spin, in this sense, is not only a driver of astrophysical events, but a laboratory for exploring the foundations of temporality. There is also a more subtle consequence. The flow of time is intimately connected with entropy, the measure of disorder in the universe. Black holes, with their immense entropy, push this concept to its limits. A spinning black hole, with its reduced horizon area, compared to a non-rotating one of the same mass, has different entropic properties. This connection suggests that time's arrow, which emerges from entropy, may itself be shaped by spin. If so, then the rotation of horizons is tied not just to astrophysics, but to the very existence of past, present, and future. We do not yet know the final answers. What we know is that spin transforms space-time in ways that strain our intuitions. It bends trajectories, it powers jets, and it warps time itself. Around the fastest spinners, the familiar certainties of chronology and causality falter, leaving us with hints of a universe stranger than we can yet grasp. Perhaps this is why black holes captivate us so deeply. They are not simply objects of mass and gravity. They are stages where the rules of reality perform their most extreme dramas. Spin, in particular, turns these dramas into paradoxes, where time may circle, where causes and effects blur, and where the edge of knowledge becomes visible. As we step from this chapter to the final reflections, we carry with us the realization that spin is not only an astrophysical quantity, it is a key to the nature of time itself. And if time is the canvas on which the universe paints, then spin is one of the brushes, shaping the strokes that define existence. From the moment we first imagined black holes, they were mysteries. They began as mathematical shadows in the equations of Einstein, thought to be curiosities with no place in the real universe. Yet the cosmos proved otherwise. Stars collapsed, horizons formed, and telescopes found their silent signals in X-rays, radio waves, and gravitational ripples. In every discovery, spin has been there not only as a number in equations, but as the rhythm of the universe itself. Spin tells the story of collapse. A star that rotates even gently will pass its angular momentum into the black hole it becomes, ensuring that no horizon is ever truly still. Spin tells the story of growth. Accretion disks feed black holes and spin them up, pushing them toward the Kerr limit. Mergers fuse horizons and redistribute angular momentum, leaving behind new spinners that carry echoes of their parents. Spin tells the story of power. It fuels jets, lights, quasars, and sculpts galaxies. And spin tells the story of mystery. It shapes time, bends causality, and plays a role in the paradox of information itself. And yet, after all these stories, one truth remains. We do not fully understand why the universe permits some black holes to spin so close to the speed of light, nor whether any ever reach extremality. We cannot see beyond the horizon, cannot follow information as it falls inward, cannot reconcile relativity with quantum rules. Spin opens doors, but behind each door lies another. It is a mystery that deepens the closer we approach. This may be the point. Some mysteries are not failures of knowledge, but invitations to wonder. Spin is not a gap in physics to be filled. It is a reminder of how much remains unknown. In every jet that pierces a galaxy, in every quasar that burns at the edge of visibility, in every gravitational wave that shakes space-time, we see the fingerprints of spin. We see both the reach of human discovery and the vastness of what is left to uncover. Perhaps spin is more than a feature of black holes. Perhaps it is a reflection of something more fundamental. The universe itself is filled with motion, from atoms spinning in quantum states to galaxies rotating in cosmic filaments. Everywhere we look, we find cycles, orbits, revolutions. Black hole spin may be the most extreme form of this cosmic dance, but it is not separate from it. It is part of a pattern as old as time, that motion and change are the essence of existence. In the end, we return to the silence of horizons. Black holes spin, but they do not speak. Their stories are told in the light of matter that falls toward them. In the waves of space-time they send across the cosmos. In the structures they sculpt on galactic scales. We measure, we model, we imagine, yet the black holes remain silent, turning endlessly in the dark. Their spin is both revealed and hidden, both measured and unknowable. It is an eternal mystery, and perhaps it always will be. The more we learn about spin, the more it becomes a mirror. It reflects back not only the physics of collapse and accretion, but the deeper limits of human knowledge. Every observation, every simulation, every theory brings us closer to understanding, but also reminds us how vast the unknown still is. Spin shows us that the universe is not static. It is restless, dynamic, filled with hidden rotations that shape everything from the smallest particles to the largest galaxies. In the ergosphere of a spinning black hole, energy can be extracted from the very fabric of space-time. In the jets of quasars, we see rotation amplified into structures that stretch across millions of light years. In the ripples of gravitational waves, we hear the echoes of horizons merging and spinning as one. Spin is written into the cosmos as rhythm and motion, as pattern and power. Yet behind its physical effects lies a silence that humbles us. For all that we can measure, the inner truth of a black hole's spin remains forever hidden behind the horizon. Some mysteries in science are temporary, waiting for the right instrument or theory. Others may be permanent, woven into the structure of reality. Black hole spin feels like both. With new telescopes, we will map it across the universe, tracing histories of galaxies and stars. With new theories, we will connect it to quantum gravity and the paradox of information. Yet even as we do, the core will remain veiled. Spin belongs to horizons we cannot cross, to regions where space-time folds in on itself. Its full truth may be forever inaccessible, and that is part of its power. But mystery need not be despair. Mystery is the seed of wonder. It drives us to ask, to build, to explore. When we stare at a galaxy whose center burns with a jet, when we detect the whisper of space-time ringing from a merger, 1 billion light-years away, when we imagine the fabric of time itself twisting around a horizon, we are sharing in the mystery. We are reminded that the universe is larger than our comprehension, and that its deepest truths are not only equations, but experiences of awe. Perhaps, in the end, the eternal mystery of spin is not meant to be solved completely. Perhaps it is meant to be lived with a reminder that the universe is both knowable and unknowable, measurable, yet infinite. Black holes will keep spinning, near the speed of light, indifferent to whether we ever unlock their secrets. They will shape galaxies, power quasars, stir clusters, and carry with them the memory of stars long gone. And we, for our part, will continue to watch, to listen, and to wonder. The last word belongs not to us, but to the cosmos itself. In the silent turning of black holes, we glimpse the rhythm of existence, the eternal dance of matter and time. Spin is not just a property of black holes. It is a symbol of the universe in motion, a whisper that reality itself is never still. And so the mystery endures, eternal, unreachable, and yet endlessly inviting, drawing us forward into the dark, where the answers wait beyond the horizon. When we step back and view the story of black holes from beginning to end, what emerges most clearly is the legacy of spin. It is not an afterthought, not a minor parameter tucked into equations. It is a central force in the unfolding drama of the universe. Every black hole, from the smallest remnant of a collapsed star to the giants weighing billions of suns at galactic centers, carries with it the rotation inherited from its birth. And that rotation does not vanish into silence. It leaves marks everywhere in the light we see, in the jets we trace across galaxies, in the gravitational waves that shake the fabric of space-time itself. Spin tells us about death and rebirth. When a star reaches the end of its life and collapses, its angular momentum cannot simply disappear. The core shrinks, the rotation speeds up, and if the collapse continues past the neutron star stage, the result is a black hole. The rotation of the progenitor lives on in the spin of the horizon. In this way, spin is the memory of stars. It preserves in silence the histories of lives that ended millions or billions of years ago. Spin also tells us about growth. Black holes are not static tombs. They are dynamic engines, fed by the gas of companions, by the fall of interstellar clouds, by the mergers of galaxies. Each moment of feeding shapes their spin, either adding to it or slowing it, depending on the direction of the flow. Accretion disks act like giant wheels, passing angular momentum inward until it becomes locked behind the horizon. In this way, spin is a ledger, a record of cosmic transactions written in space-time itself. Spin tells us about power. Without it, black holes would still consume matter and grow, but their influence on galaxies would be quieter, their signatures less dramatic. With it, they ignite into quasars, blasting radiation across billions of light years. With it, they hurl jets of plasma that stretch far beyond their galaxies, carving radio lobes into the intergalactic medium. With it, they regulate the cooling of gas in clusters, determining how stars form and galaxies evolve. Spin is not passive. It is active, an engine of feedback that ties the smallest scales of physics to the largest structures in the universe. And spin tells us about mystery. Around rotating black holes, time bends and frames drag. Paths that defy common sense become real. Energy can be extracted from the ergosphere. Particles can split and emerge with more than they had. And the horizon itself becomes a laboratory for testing the limits of relativity. At the extreme, spin brushes the edge of causality, threatening paradox and inviting questions that reach into quantum gravity. No other parameter carries us so far toward the frontier of knowledge. The legacy of spin, then, is both practical and profound. It is written in the X-ray spectra of binaries, in the light curves of quasars, in the radio lobes of galaxies, in the ripples of gravitational waves. It is written, too, in the equations of Kerr geometry, in the paradoxes of information, in the speculations of string theory. From observation to theory, from astrophysics to philosophy, spin links the parts of the cosmos into one coherent story. And perhaps the most remarkable part of this legacy is how quickly we have come to see it. Barely a century ago, black holes were abstractions. Barely a decade ago, we had no direct way to measure spin. Now we do, with X-ray telescopes, with interferometers stretching across continents, with global collaborations imaging horizons themselves. Humanity has reached into the silence of black holes and found rhythm there. A rhythm measured not with sound, but with light and gravity. What we have uncovered so far is only the beginning. The legacy of spin will grow with every new detection, Every new survey, every new image, each will add to the record, showing us not only how black holes shape the universe, but how the universe itself remembers. For spin is memory, the memory of stars, of galaxies, of cosmic history itself, and it is a legacy that endures, turning endlessly beyond the horizon, even when no eye can see and no ear can hear. Spin is not unique to black holes. It is a universal rhythm, woven into the fabric of nature on every scale. From the smallest particles to the largest galaxies, the universe is filled with cycles, rotations, and revolutions. What makes black holes special is that they take this rhythm to its extreme, compressing it into the tightest possible whirl of space-time. Yet when we look closely, we see that spin is not an isolated phenomenon. It is connected to the patterns of the cosmos itself. At the smallest scales, electrons spin. This intrinsic angular momentum is a quantum property, one that cannot be explained by imagining a particle physically rotating, but instead arises from the mathematics of quantum mechanics. Without it, atoms would not hold together, chemistry would not exist, and life itself would not emerge. Spin, at this level, is a foundation of matter. It is the quiet law that underlies everything, solid, liquid, and living. At larger scales, planets spin on their axes and orbit their stars. Stars themselves rotate, sometimes slowly, sometimes furiously, their spin influencing their evolution and magnetic activity. Galaxies whirl like cosmic pinwheels, their spiral arms held together by rotation and gravity. Everywhere we look, we see spin in clouds of gas that collapse into stars, in storms that circle on worlds, in the subtle procession of pulsars. The universe is not still, it is restless, turning endlessly. Black hole spin may be the most extreme version of this restlessness, but it is not separate from it. It is part of the same tapestry. The collapse of a star that produces a black hole is simply the continuation of rotation into a new regime, where gravity overwhelms all other forces. The spin of the black hole is the preserved echo of the star's motion, transformed into the rotation of space-time itself. In this way, black hole spin is not alien. It is kin to the motions we know, taken to their ultimate conclusion. Some physicists wonder if this ubiquity of spin points to something deeper. Could rotation be fundamental to reality itself, not just an accident of collapsing clouds or orbiting stars? Could it be that the universe has its own intrinsic spin, perhaps encoded in the way space-time expands, or in the way galaxies align along filaments of the cosmic web? While no evidence yet proves such cosmic rotation, the question itself arises naturally from the patterns we see. Spin is everywhere. Why not in the universe as a whole? Even in the unknown domains of physics, spin whispers connections. Dark matter, which shapes the growth of galaxies, may interact differently depending on angular momentum. Dark energy, the force driving cosmic expansion, may yet be tied to hidden symmetries that involve rotation. And in the search for a theory of quantum gravity, spin shows up again, linking black holes to holography, string theory, and the microstates of entropy. Wherever we push our theories, spin follows, as though it is a thread running through the entire fabric of reality. Perhaps this is why spin feels so mysterious. It is both specific and universal, both measurable and enigmatic. We can calculate the spin of Cygnus X1 or infer the rotation of M87 star, but at the same time we sense that spin belongs to a wider order, one that connects black holes to electrons, galaxies, and perhaps even the cosmos itself. In the whirl of horizons, we glimpse the same rhythm that animates storms, planets, and atoms. It is as though the universe is reminding us that motion, not stillness, is its true state. Black holes do not exist apart from this. They are not exceptions. They are intensifications. They take the universal rhythm of spin and magnify it, showing us what happens when motion collides with gravity at its strongest. And in doing so, they reveal that the hidden connections of spin may be the key to understanding not only black holes, but the entire cosmos. The story of spin is not finished. Even now, as telescopes scan the skies and interferometers listen to space-time, the future of discovery stretches before us. Every advance in technology reveals new ways to measure and interpret spin, and every new measurement raises deeper questions. The horizon of understanding is not fixed. It recedes as we approach, beckoning us onward. The next generation of observatories promises to transform spin from a rare measurement into a common one. Athena, the advanced telescope for high-energy astrophysics, will examine the X-ray light from accretion disks with unprecedented clarity, sharpening the signatures of broadened ion lines and thermal continua. Where today we have dozens of spin values, tomorrow we may have thousands, spanning the universe from nearby binaries to distant quasars. With these data, we will begin to map the distribution of spins across cosmic history, tracing how black holes have grown over billions of years. The Laser Interferometer Space Antenna, or LISA, will add a new voice to this chorus. From its orbit around the Sun, this gravitational wave observatory will detect the mergers of supermassive black holes across the universe. These signals will carry the fingerprints of spin in the inspiral, the merger, and the final ringdown. With LISA, we will hear the deep tones of space-time itself, and through them, measure spins with a precision impossible by any other means. Each detection will be a story of two horizons colliding, their spins entwining, their legacies merging into one. The Event Horizon Telescope, too, will evolve. Its next generation will sharpen its vision, imaging horizons with higher resolution and across multiple wavelengths. Already we have seen the shadows of M87 star and Sagittarius A star. In the future, we may see dozens more, each shaped by the spin of the black hole at its center. The bending of light, the brightness of crescents, the orientation of jets, all will become clearer, allowing spin to be read directly from images of space-time itself. Beyond instruments, theory continues to press outward. Numerical relativity grows more sophisticated, modeling not only mergers but also the turbulent flows of magnetized plasma in accretion disks. Quantum gravity explores extremal black holes as laboratories for uniting relativity with the quantum world. Even the black hole information paradox continues to evolve, with new proposals that tie the preservation of information to the structure of horizons shaped by spin. In every direction we push, spin is there, a constant presence, guiding and complicating our search for understanding. And then there is the possibility of the unknown. What if new physics waits at the edge of the Kerr bound? What if spin values just above unity exist in the universe, not as stable black holes, but as exotic objects, naked singularities, gravastars, or phenomena we have yet to name? What if spin reveals links to dark matter, dark energy, or new symmetries of space-time? These questions are not fantasies. They are the natural extension of the mysteries we already face, the puzzles raised by every black hole we observe. To study spin, then, is to step toward new horizons. It is to accept that the universe has more to show us, that the line between the known and the unknown is not fixed, but shifting. Each new telescope, each new detection, each new theory carries us closer, not to final answers, but to deeper questions. Spin is not only a measurement, it is an invitation. And as we look ahead, we realize that this invitation is not just for scientists, it is for humanity itself. To trace spin is to trace the rhythm of the cosmos, to see in the turning of horizons the echo of motion everywhere. It is to remember that we are part of this universe, and that its mysteries are also ours. In the silence of the night sky, black holes continue their endless turning. We cannot hear them, but we see their echoes in the light of quasars, in the arcs of jets, in the trembling of space-time when horizons collide. Their spin is not only a property of gravity, it is a language one that the universe speaks through cycles and rhythms, through collapse and rebirth, through silence and motion. We have followed spin from the collapse of stars to the shaping of galaxies, from the bending of light to the stretching of time, from the paradox of information to the possibilities of new physics. We have seen that spin is both a fact and a mystery, both measured in observatories and hidden forever behind horizons. It powers some of the brightest beacons in the cosmos, and also conceals the deepest secrets of reality. And in the end, spin leaves us with a lesson. The universe is not still, it is restless, dynamic, alive, with motion. From electrons to galaxies, from storms on planets to the whirl of horizons, everything turns. Black hole spin is the most extreme expression of this truth, but it is not alone. It is a reminder that to exist is to move, to change, to dance in time with the cosmos. Perhaps we will one day resolve every paradox, measure every horizon, and unify every law. Perhaps not. But either way, spin ensures that mystery will remain. There will always be horizons we cannot cross, truths we cannot fully hold. Black holes will keep turning, whispering across the void that the universe has secrets it will never surrender. That is the eternal invitation of spin, not to solve everything, but to keep searching, to keep wondering, to keep reaching beyond the limits of what we know. For in that search lies the very essence of being human. And so the book ends where the cosmos continues, with black holes still spinning in silence, shaping galaxies, shaping time, shaping the future. They will outlast stars, outlast galaxies, outlast us. And as long as they turn, they will carry within them the rhythm of the universe, a rhythm that calls us to listen, to imagine, and to dream beyond the horizon of understanding.